Previously on Science Answers. A journey through space and time, the origins of everything. From the dawn of space and time, we traveled back 13.7 billion years to witness the Big Bang, the fiery birth of everything. As the universe cooled, the first atoms formed, leading to vast hydrogen clouds and the birth of the first stars. These ancient beacons illuminated the darkness, ending the cosmic dark ages. The Milky Way took shape, housing billions of stars, including our very own Sun, which ignited from a swirling solar nebula 5 billion years ago. Around it, the planets of the solar system emerged, rocky worlds like Earth and Mars, and gas giants like Jupiter and Saturn. Earth transformed into a cradle of life, surviving the late heavy bombardment and evolving through time. From microscopic organisms to the Cambrian explosion, life flourished. But Earth also faced mass extinctions, including the asteroid impact that ended the age of dinosaurs. Across human history, civilizations looked to the stars. Babylonians, Egyptians, Greeks, and Chinese astronomers mapped the heavens, unlocking the secrets of the cosmos. From ancient myths to Ptolemy's geocentric model and Copernicus's heliocentric revolution, our understanding of the universe grew. Now we continue the journey, exploring deeper mysteries, cosmic frontiers, and the next great questions of existence. Welcome to Season 2, From Chaos to Order.
Enceladus. English astronomer William Herschel, dissatisfied with solely directing his increasingly powerful telescopes at the recently discovered Uranus, commenced his pursuit of new moons orbiting Saturn. In August 1789, the discovery of Saturn's sixth moon brought him recognition, and nearly 60 years later, Herschel's son, John, designated the moon Enceladus, after a legendary Greek giant. Centuries of telescope observations of Enceladus have disclosed minimal information about the moon, specifically its orbital period, 1.4 days, its remarkable brightness, reflecting nearly 100% of sunlight from its surface, and its apparent connection to Saturn's E-ring. Nonetheless, spectroscopy of Enceladus revealed indications of extremely fine-grained water ice. The Voyager flybys of 1980 and 1982, along with the Cassini-Saturn orbiter mission initiated in 2004, have elucidated the authentic characteristics of this peculiar and fascinating celestial body. Measuring approximately 310 miles, 500 kilometers, in diameter, it nonetheless showcases some of the most diverse geological landscapes in the solar system. Certain regions of Enceladus are extensively cratered and ancient, while others exhibit minimal cratering, indicating they are geologically youthful. Certain locations exhibit profound troughs, abrupt ridges, or acute grooves, indicating the influence of substantial tectonic forces. Nevertheless, the most exhilarating finding has been the identification of active plumes of water vapor emanating from the south polar region of Enceladus. Navigating the Cassini probe through these plumes revealed trace quantities of nitrogen, methane, carbon dioxide, propane, ethane, and acetylene. This suggests that Enceladus is expelling ice and organic compounds into space, akin to a colossal comet rather than a satellite moon. What is the impetus behind the activity occurring on and within Enceladus? The 1.6 grams per cubic centimeter density indicates that certain rocky materials are appropriate for radioactive heating. Like Io, Europa, and Ganymede, it undergoes tidal heating due to its orbital resonance with Dione. Data from Cassini demonstrate the potential existence of a saline subsurface liquid water layer, an ocean, beneath the icy crust. Astrobiologists are observing attentively. Mimas. In September 1789, William Herschel discovered the seventh known moon of the ringed planet shortly after identifying Enceladus. At that time, this latest satellite was the nearest to Saturn, possessing an orbital period of under 1 day. John Herschel, the son of William, subsequently named this moon Mimas after a giant from Greek Titan mythology. Herschel's groundbreaking telescope designs, proficient in gathering an extraordinary quantity of photons from remote sources, allowed him to identify dim moons near luminous planets. He used a 40-foot, 12-meter reflecting telescope featuring a primary mirror with a diameter of 4 feet, 1.2 meters, to discover Mimas and Enceladus, rendering it the largest telescope globally. Telescopic spectroscopy of Mimas revealed a surface predominantly composed of water ice, similar to all other Saturnian moons except Titan. Limited information existed regarding Mimas until the Voyager and Cassini spacecraft missions acquired detailed images and additional data. The images disclosed that Mimas is a diminutive celestial body measuring approximately 250 miles, 400 kilometers in diameter, less than 1/8 the size of Earth's moon, with a density slightly below 1.2 grams per cubic centimeter, suggesting a predominantly icy composition. Astronomers contend that Mimas is near the minimum size for an astronomical body capable of achieving a spherical configuration due to its self-gravity. Mimas is distinctly oblate, being approximately 10% broader at the equator compared to the poles due to the significant gravitational influence of the adjacent Saturn. Herschel used his 40-foot, 12-meter telescope to identify Mimas and Enceladus. Mimas displays considerable cratering, though not uniformly. Canyons and fractures indicate that tectonic forces or cryovolcanism may have resurfaced in certain regions in the remote past. Mimas is characterized by a singular colossal crater that spans nearly 1/3 of the moon's diameter, imparting it a notable Death Star appearance. Meteorites are derived from outer space. Although it was frequently presumed that rocks occasionally descended from the sky, this concept was deemed ludicrous for much of human history. During the late 18th and early 19th centuries, scientists found numerous ancient and indigenous cultures recognize that specific stones exhibiting peculiar magnetic properties or elevated iron metal concentrations originated from the main belt and nearby asteroids. In 1794, German physicist Ernst Chladni posited that certain unique rocks, including a metal-rich specimen he examined known as the Pallas iron, which was discovered in 1772 near the Russian city of Krasnoyarsk, originated from outer space. Numerous scientists deemed the concept remarkable, asserting that these rocks were either volcanic or generated by lightning strikes. By the early 19th century, comprehensive laboratory analyses of these rocks became feasible. In 1703, French physicist and mathematician Jean-Baptiste Biot corroborated Chladni's hypothesis by showing that the chemical compositions of numerous rocks found near L'Aigle after a remarkable meteor shower were unlike any known terrestrial rocks. These rocks were designated as meteorites, leading to the emergence of the scientific discipline of meteoritics. Researchers have amassed over 30,000 meteorites globally, predominantly from barren deserts or Antarctic ice fields, where it is comparatively simple to identify an unusual rocky intruder that has descended from the sky. The predominant composition of rocks that fall to Earth, 86%, consists of simple silicate minerals and minute spherical grains known as chondrules, which are believed to be among the earliest materials condensed from the solar nebula and serve as the foundational elements of asteroids and, ultimately, planets. Approximately 8% of the meteoritic material that descends to Earth consists of silicates devoid of chondrules, representing samples of igneous rocks from the previously geologically active crusts of substantial asteroids, the Moon and Mars. Merely 5% of the land comprises iron and iron-nickel, akin to the rocks initially examined by Chladni and Biot. These rocks are remnants of the cores of ancient, now fragmented asteroids and planetesimals, which had attained sufficient size to differentiate into core, mantle, and crust before their destruction by impacts during the tumultuous early history of the solar system. In 2008, researchers identified a 14-ounce, 408-gram, ordinary chondrite meteorite on the firm, gravelly terrain of the Rub al-Khali Desert near Ash-Shaqiya, Saudi Arabia. The dark exterior is a slender fusion crust created during the rock's brief, intense transit through Earth's atmosphere. Comet Encke. Notwithstanding considerable advancements in fostering gender equity in science in recent decades, men have predominantly influenced the historical narrative of astronomical observations and discoveries from antiquity. One of the initial female pioneers to infiltrate this male-dominated sphere was the English astronomer Caroline Herschel, the younger sibling of William Herschel, the discoverer of Uranus. Caroline was a proficient vocalist and frequently performed in concerts alongside her brother during their youth. Her fascination with astronomy coincided with William's, and as he increasingly dedicated his time to telescope construction and observations, she accompanied him as a steadfast assistant. She attained expertise in astronomical calculations and established a reputation that surpassed her brother's as a mirror polisher and telescope engineer. In 1782, prompted by her brother, she commenced her observations. The younger Herschel primarily concentrated on comet discovery, identifying 8 throughout her career. In 1819, the German astronomer Johann Encke identified the comet she discovered in 1795 as the second known periodic comet, following Halley's. Comet Encke is renowned among astronomers for possessing the shortest orbital period of all known periodic comets, completing its revolution around the Sun in merely 3.3 years. Due to its relatively frequent occurrences, it is among the most extensively researched comets. Caroline Herschel published a significant star catalogue in 1798 and discovered Messier 110, a companion to the Andromeda Galaxy. Before that time, she was broadly acknowledged as the preeminent female astronomer. She was one of the inaugural women granted honorary membership in the Royal Astronomical Society, with a subsequent 80 years passing before women were permitted full membership. She left an indelible mark as a proficient observer and a paragon for women pursuing scientific careers in a domain historically dominated by men. Ceres. The late 18th century discovery of Uranus and numerous new solar system moons prompted astronomers to engage in more meticulous cataloging and exploration of the heavens. One of the most meticulous and methodical sky mappers was the Italian priest, mathematician, and astronomer Giuseppe Piazzi from the Palermo Astronomical Observatory. From 1789 to 1803, Father Piazzi supervised the compilation of the Palermo star catalogue, documenting nearly 8,000 stars. During his cataloging efforts on January 1, 1801, Piazzi observed a faint 8th magnitude star near the head of the constellation Cetus that had not been recorded in earlier catalogues. In the subsequent nights, he observed its movement relative to the stationary stars and speculated that he may have identified a comet. However, the absence of a comet-like coma or tail prompted him to hypothesize that it could be something superior. Subsequent observations by Piazzi and others culminated in the late 1801 discovery that the star-like object was, in fact, orbiting the Sun as a planet, situated between Mars and Jupiter, approximately 2.7 astronomical units away. Piazzi designated it Ceres Ferdinandia, in honor of the Roman goddess of agriculture and his benefactor, King Ferdinand III of Sicily. Astronomers were uncertain about the classification of Ceres, too diminutive and faint to be categorized as a planet, yet not fitting the definitions of a star, comet, or moon. In 1702, astronomer William Herschel introduced the term asteroid, star-like, to refer to Ceres and the recently identified Pallas. Contemporary telescopic observations indicate that Ceres is the largest asteroid in the main belt, possessing a diameter of approximately 590 miles, 950 kilometers, and a density of about 2 grams per cubic centimeter, implying the potential existence of an ice-rich interior. Astronomers currently categorize Ceres as a dwarf planet, akin to Pluto, owing to its dimensions and capacity to assume a spherical form under gravitational influence. The NASA Dawn mission provided extensive insights into the surface and interior of Ceres upon its arrival in March 2015. Notable findings encompass identification of primordial ice volcanoes and basic organic compounds on the asteroid's exterior. Astronomers have ascertained the trajectories of over 750,000 asteroids as of mid-2018, anticipating a significant increase in this figure. As more comprehensive surveys identify fainter objects, the solar system is abundant with minor planets. Vesta. After discovering Ceres in 1801, scientists promptly identified a second asteroid, Pallas, in 1802 and a third, Juno, in 1804. The German astronomer Heinrich Wilhelm Olbers contributed to 2 discoveries: the recovery of Ceres near its anticipated location in late 1801, and the discovery and nomenclature of Pallas in 1802. Olbers, a physician during the day and an astronomer at night, posited that minor planets like Ceres and Pallas might be the remnants of a previously extant planet that was destroyed and likely existed between Mars and Jupiter. In 1707, Olbers identified the 4th recognized asteroid while searching for additional potential planetary fragments. The mathematician Carl Friedrich Gauss computed its orbit and designated it Vesta in honor of the Roman Virgin goddess of the hearth. Gauss discovered that Vesta, similar to Ceres, Pallas, and Juno, orbits within the main asteroid belt, which extends from approximately 2.1 to 3.3 astronomical units, AU, and is centered around 2.7 AU. Since astronomers have established that Ceres, Pallas, Juno, and Vesta constitute approximately 50% of the total mass of the main asteroid belt, it is unsurprising that early 19th century astronomy textbooks frequently designated them as new planets. Currently, they may be referred to as dwarf planets. Vesta is the most luminous asteroid in the primary asteroid belt. The Hubble Space Telescope and NASA's Dawn mission have observed it from Earth and determined that it measures approximately 330 miles, 530 kilometers in diameter, possesses a rocky density of 3.4 grams per cubic centimeter, and exhibits a flattened shape due to 2 large impact basins originating from the asteroid's south pole. Spectroscopic data suggests that the asteroid was once molten and differentiated into a core, mantle, and volcanic crust akin to terrestrial planets. Meteorites belonging to the Howardites, Eucrates, and Diogenites classes are likely fragments of Vesta ejected by significant impacts at the South Pole. The Dawn mission delivered essential information regarding Vesta's geology, composition, and history during its year-long orbital mission around Vesta from 2011 to 2012. The asteroid has been identified as a rare surviving specimen of an ancient transitional entity referred to as a protoplanet, part asteroid, part planet. Vesta is essential for understanding the formation of terrestrial planets like Earth. Isaac Newton's experiments in 1672 revealed that sunlight is not merely white or yellow, but a spectrum of various colors that refract differently when traversing an object, such as a prism. Other individuals, including English scientist William Hyde Wollaston, extensively reiterated and elaborated on Newton's experiments, becoming the first to identify enigmatic dark lines in certain regions of the sun's spectrum in 1802. Scientists required a tool or method to comprehend these dark lines and their precise locations within the solar spectrum. In 1814, German optician Joseph von Fraunhofer invented a spectroscope. A novel experimental technique termed spectroscopy may employ this specifically engineered prism to ascertain the positions or wavelengths of the spectral lines. Utilizing his spectroscope, he detected over 500 dark lines in the solar spectrum, which astronomers continued to designate as Fraunhofer lines. In 1821, he developed a higher resolution spectroscope employing a diffraction grating rather than a prism. He established stellar spectroscopy by identifying that luminous stars like Sirius possess spectral lines distinct from those of the Sun. By the mid-19th century, physicists and astronomers could replicate these lines in the laboratory by passing light through different gases. Consequently, they found that various atomic elements absorb distinct, narrow, and specific light wavelengths, resulting in lines forming. Utilizing spectroscopy to ascertain the atomic and molecular composition of distant light sources, such as the Sun, planetary atmospheres, stars, and nebulae, necessitated only a telescope and a spectrometer. This was achievable without direct contact with the objects. Spectroscopy from terrestrial and extraterrestrial telescopes, and from orbiting and landing missions to other celestial bodies, constitute a crucial component of contemporary astronomy and space exploration. Parallax refers to the perceived motion of an object resulting from the observer's shifting viewpoint. Position a finger before your face and alternate blinking between your left and right eyes. The apparent movement of your finger is due to the slight alteration in viewing perspective, known as parallax. A comparable experiment can be conducted by utilizing a significantly larger alteration in viewing perspective, the diameter of the Earth's orbit, to investigate parallax motions among the stars and consequently ascertain their distances from us. From the era of Aristarchus to that of Tycho, astronomers utilized the absence of observable parallax for any star as evidence that the Earth was stationary at the center of the universe. After establishing Copernicus's heliocentric model, astronomers referenced the persistent inability to measure stellar parallax as proof of the star's vast distances. To what extent? Friedrich Wilhelm Bessel, a German mathematician and distinguished stellar cartographer, successfully measured a star's parallax in 1838. He employed observations 6 months apart, when Earth was positioned on opposite sides of the Sun, to ascertain a parallax of 0.314 arc seconds, 0.000087 degrees, for the star 61 Cygni. Bessel estimated the distance to 61 Cygni to be approximately 58 trillion miles, 93 trillion kilometers, based on a change in viewing perspective of 2 astronomical units, 186 million miles, 300 million kilometers, which is nearly 10 years' travel at the speed of light. Bessel's estimate approximated the contemporary accepted value of 11.4 light-years. In 1838, astronomers Georg Wilhelm Struve and Thomas Henderson similarly reported parallax findings, resulting in distance estimates of 25 light-years to Vega and 4.3 light-years to Alpha Centauri. Alpha Centauri exhibits one of the most significant observed proper motions in the celestial sphere and is recognized as the star system nearest to the Sun, situated at approximately 272,000 times the Earth's mean orbital distance. Even the nearest stars are exceedingly distant. The most accomplished astronomers prior to the 19th century were also skilled artists out of necessity. They could document their observations solely through sketching, drawing, or painting what they perceived visually. Nevertheless, circumstances rapidly transformed with the advent of photography in 1839. Advancements in photographic techniques would ultimately transform astronomy. Primitive photographic techniques were unwieldy, rudimentary, and hazardous. The daguerreotype process, created by French inventors Louis Daguerre and Joseph Niepce, could generate comparatively sharp images on wet copper plates coated with silver. The process necessitated that photographers collaborate intimately with hazardous mercury, iodine, or bromine vapors. Nonetheless, the remarkable outcomes prompted the French government to promptly make the process publicly accessible worldwide at no cost following its inception. John William Draper, an American physician, chemist, and photographer, rapidly enhanced Daguerre's process. His scientific interests motivated him to direct his apparatus toward the sky, resulting in a succession of progressively higher quality daguerreotype plates of the Moon from 1839 to 1843. Draper's lunar plates constituted the inaugural documented images of a discernible astronomical entity. The invention of dry plate technology in the 1870s facilitated the emergence of astrophotography as a significant scientific research instrument for capturing images and spectra. Henry Draper, son of John Draper, perpetuated his father's legacy in astrophotography by affixing his cameras to large telescopes, capturing the inaugural photographic spectrum of the star Vega in 1872, and obtaining the first photograph of the Orion Nebula in 1880. Film ultimately supplanted plates. However, analog photographic technology attained its sensitivity threshold in the mid-20th century. The 1970s witnessed the advancement of electronic imaging technology, notably the charge-coupled device, which currently functions as the favored photographic medium for scientific and consumer purposes. In the decades after its discovery in 1781, astronomers meticulously monitored the position and refined the orbit of the languid planet Uranus. Several minor discrepancies were observed between the predictions of Newton's law of gravity and its actual trajectory in the sky. The English astronomer John Couch Adams and the French mathematician Urbain Le Verrier, both exceptionally skilled theorists, hypothesized that the gravitational influence of an invisible planet could account for these discrepancies. In 1845 and 1846, Le Verrier and Adams independently formulated predictions regarding the potential location of Uranus's hypothesized perturber in the celestial sphere. Adams persuaded his colleagues at Cambridge to pursue the planet's discovery. However, the observers merely identified it as a star amidst vast expanses of sky. Conversely, Le Verrier's prediction pertained to a more limited sky area. In a matter of hours, on September 24th to 25th, 1846, his associate, the German astronomer Johann Galle, located it at the Berlin Observatory and subsequently confirmed its designation as the eighth planet over several additional nights. The French mathematician and politician François Arago lauded the discovery as a victory for Newtonian physics, asserting that Le Verrier had identified a planet with the point of his pen. A magnanimous Adams and others collectively acknowledged Le Verrier and Galle for the discovery of the new planet. Le Verrier designated it Neptune, named after the Roman deity of the sea. Its discovery further augmented the solar system's dimensions. Neptune, with an average orbital distance of 30 astronomical units and an orbital period of approximately 165 years, exhibits a small apparent diameter and rapid motion which elucidates why several earlier astronomers, including Galileo, observed Neptune but, similar to Adams's colleagues at Cambridge, failed to identify it as anything beyond a mere bluish star. Only one space mission, the Voyager 2 flyby in August 1989, has examined Neptune in detail, providing scientists with a brief view of a stunning and tempestuous blue planet in the distant outer regions of our solar system. Triton. The discovery of Neptune in autumn 1846 presented a new objective for lunar explorers, posing a challenge due to Neptune's vast distance from the Sun. William Lassell, a British merchant and amateur-turned-professional astronomer, identified Neptune's moon merely 17 days following the discovery of Neptune. Lassell accumulated his wealth as a brewer and utilized it to construct telescope mounts, polish his mirrors, and assemble a 24-inch, 61-centimeter Newtonian reflector, which was, at that time, the largest operational telescope in the world. Upon learning of Neptune's discovery, John Herschel proposed to Lassell that he utilize his telescope to investigate the presence of moons orbiting the newly discovered planet. Lassell discovered a peculiar moon after merely 8 days of searching. Observations of its orbit indicated it was moving retrograde relative to all known moons in the solar system. Moreover, its orbit displays a significant inclination relative to Neptune's orbital plane, resulting in each pole periodically orienting nearly directly towards the Sun, similar to a severely tilted Uranus. Lassell did not designate a name for his discovery. Astronomers subsequently concurred on Triton, the Greek sea deity and offspring of Poseidon, the Greek counterpart of Neptune. Prior to the Voyager 2 encounter in 1989, scant information existed regarding the remote moon Triton. Subsequently, it was found to possess a substantial diameter of 1,678 miles, 2,700 kilometers, a high albedo of 70 to 80%, and an icy, rocky density of 2.1 grams per cubic centimeter. Researchers unexpectedly found a tenuous nitrogen atmosphere, softly erupting geysers, and a geologically youthful surface characterized by a scarcity of craters perpetually renewed through icy cryovolcanism. Recently, nitrogen, water, and carbon dioxide, which exist at temperatures only 30 to 40 degrees above absolute zero at the surface but may be heated by radioactive processes in the interior, have formed Triton's peculiar landforms. Numerous astronomers contend that Triton, akin to Pluto, originated in the Kuiper Belt and was subsequently captured by Neptune, resulting in its inclined retrograde orbit. Despite the groundbreaking contributions of English astronomer Caroline Herschel in paving the way for women in science and astronomy during the late 18th century, only a limited number of women could successfully pursue this path for an extended period. It would take more than 50 years for the first female scientist to establish a professional academic career in astronomy. Maria Mitchell, a native of Nantucket, was a proficient observational astronomer and educator. Mitchell assisted in teaching at a school established by her father on the island and ultimately became a librarian. She absorbed the scientific and literary works of the era while furthering her experience in observing the night sky. In 1847, utilizing her father's modest observatory, she identified a faint comet discernible only through a telescope. The comet was colloquially referred to as Miss Mitchell's Comet. Mitchell's astronomical contributions received extensive acclaim. She journeyed to Europe to confer with fellow astronomers and accept accolades. A nautical almanac publisher ultimately extended an offer for her to calculate the positions of Venus. She was the inaugural female American Academy of Arts and Sciences member and the first woman elected to the American Association for the Advancement of Science. Despite her profound affection for astronomical research, she never relinquished the passion for teaching she cultivated on Nantucket. In 1865, the affluent New York entrepreneur Matthew Vassar extended a teaching position at the newly established women's university he founded, which she accepted. She was the inaugural faculty member of Vassar College and the world's first female professor of astronomy. She was appointed as the director of the Vassar College Observatory. She utilized the facility as an instructional resource for astronomy students while investigating sunspots and the varying appearances of Jupiter, Saturn, and their moons. She served on the Vassar faculty for 23 years and educated numerous women who subsequently embarked on scientific careers. Following her demise, the Society established the Maria Mitchell Initiative to preserve her legacy. In 1908, the Society inaugurated the Maria Mitchell Observatory on Nantucket, a facility still committed to astronomical education and research. Many recognize the significant alteration in the sound of an ambulance, train whistle, or race car as it approaches and accelerates away from us. As the vehicle distances itself, its sound transitions to a noticeably lower pitch or frequency than when it was approaching. This phenomenon is referred to as the Doppler effect, named after Austrian physicist Christian Doppler, who first suggested in 1842 that the perceived frequency of any wave is contingent upon the relative velocity between the wave's source and the observer. In 1845, the Dutch meteorologist C.H.D. Buys-Ballot astutely validated Doppler's hypothesis regarding sound waves by employing musicians to perform notes on a moving train, while stationary observers documented the pitches perceived as the musicians advanced and retreated. In 1848, French physicist Armand Hippolyte Fizeau demonstrated the applicability of Doppler's hypothesis to light waves by observing minor frequency variations or shifts in absorption lines within stellar spectra. Astronomers assert that the magnitude and orientation of these frequency alterations, termed Doppler shifts, can indicate the velocity at which celestial bodies converge or diverge. Objects moving towards us exhibit spectral shifts towards higher frequencies or shorter, bluer wavelengths. Conversely, objects moving away from us display spectral shifts towards red. In the 1860s, the initial precise measurements of relative stellar velocities were conducted, followed by the detection of stars' Doppler shift in the 1870s, attributed to the Earth's annual orbit around the Sun. In the early 20th century, American astronomer Vesto Slipher noted that most known nebulae, including those in Messier's catalog, exhibited redshift, indicating they were receding from us. Shortly thereafter, an American astronomer, Edwin Hubble, demonstrated that numerous nebulae were, in fact, distant galaxies, vastly removed from the Milky Way. Hubble's research directly contributed to an expanding universe and the Big Bang theory. William Herschel's identification of Mimas in 1789 resulted in a hiatus of over 50 years without discovering new moons orbiting Jupiter, Saturn, or Uranus. In late 1848, the two groups independently identified Saturn's eighth known satellite within days of one another. The American astronomers William Bond and George Bond, a father and son duo, were the first to observe the new moon. Nonetheless, the English astronomer William Lassell was the inaugural individual to declare his observations. All three astronomers received acknowledgement for the discovery. 1 year prior, John Herschel released a compendium of novel observations in which he suggested a Greek Titan nomenclature for the moons of Saturn. Lassell supported the proposal and recommended that the newly discovered moon be named Hyperion, after the Greek Titan and sibling of Cronus, the Greek counterpart of Saturn. Limited information existed regarding Hyperion, aside from its relatively eccentric orbit at an average distance of approximately 25 times Saturn's radius, well beyond the planet's ring system, until the Voyager flybys in the 1980s and the Cassini-Saturn orbiter mission's interactions with the Moon in the early 2000s. Hyperion is the inaugural and most substantial irregular non-spherical moon identified through telescopic observation. Images from the space mission reveal it to be an elongated entity, while recent telescope spectroscopy indicates that its surface consists of dark, reddish, contaminated water ice, potentially akin to that found on the dark hemisphere of Iapetus. Hyperion possesses an unusual porous surface marked by numerous deep impact craters, jagged pits, and precipices. A colossal impact crater, 75 miles, 120 kilometers in diameter, and 6 miles, 10 kilometers in depth, marks one side of the Moon. This indicates that Hyperion is merely a remnant of a more extensive satellite fragmented by a colossal impact. The density of Hyperion, measuring only 0.56 grams per cubic centimeter, suggests that it predominantly comprises highly porous water ice. Astronomers estimate that 40 to 50% of Hyperion's interior consists of voids among icy fragments. Our contemporary understanding of the planet reveals that the Earth rotates. Envision, for a brief moment, returning to a time devoid of satellites, space probes, or sophisticated computerized planetarium software and attempting to persuade an individual that the Earth is rotating. The phenomenon is counterintuitive. The sun and sky move rather than the Earth. If the Earth rotated at a velocity sufficient to complete one rotation per day, approximately 1,000 miles per hour at the equator, would we not be propelled into outer space? Even today, demonstrating the Earth's rotation to someone remains difficult. An uncomplicated and reproducible experiment is necessary to physically illustrate the Earth's rotation. In 1851, the renowned French physicist Jean-Bernard Léon Foucault conducted the most notable of these experiments. As a proficient physicist, Foucault comprehended Newton's laws and utilized the first law: an object at rest or in motion remains so unless influenced by an external force, for his experiment. He fabricated an elongated, substantial, stable pendulum utilizing a lead-coated brass bob, suspended by a 220-foot, 67-meter wire from the ceiling to the floor of the Pantheon in Paris. Foucault understood that in the absence of external influences, once the pendulum was set in motion, it would persist in oscillating within the same plane, remaining in the same inertial reference frame relative to the fixed stars rather than the Earth. By establishing hour markers akin to those on a sundial, or minor impediments for the bob to displace, and by accounting for friction in the wire or from the bob's movement through the air, it became straightforward to illustrate that the room, indeed the entire Earth, was gradually rotating about the plane of the pendulum's oscillation. In the subsequent year, Foucault refined a gyroscope utilizing analogous principles. The straightforward design of Foucault's pendulum rendered it a phenomenon in the 19th century, and numerous examples can still be found in universities, museums, and science centers globally. William Lassell, a British industrialist, brewer, and amateur astronomer, achieved considerable renown for discovering Neptune's large moon, Triton, in 1846, and his co-discovery of Saturn's small moon, Hyperion, in 1848. He innovated telescope mounting techniques, refining the equatorial mount design still utilized for numerous large telescopes, and advanced mirror fabrication and polishing methods, enabling these discoveries from a relatively modest and frequently overcast observatory named Starfield, located near his residence in Liverpool, England. William Herschel, a compatriot of Lassell, discovered the moons of Uranus, Titania, and Oberon in 1787, utilizing a lens with a diameter of 18.5 inches, 47 centimeters. Nevertheless, the last 60 years have produced no new findings on Uranian satellites. Consequently, Lassell anticipated discovering fainter moons, potentially closer to Uranus, when he directed his 24-inch, 61-centimeter Newtonian reflector, then the largest operational telescope globally, toward the Uranian system in 1851. His perseverance yielded results, leading to the discovery of 2 new moons orbiting the 7th planet. In 1852, his associate John Herschel designated them Ariel and Umbriel, after fictional characters from the works of both Pope and Shakespeare. In January 1986, the Voyager 2 space probe's flyby of the Uranus system enabled it to obtain high-resolution images of the sunlit southern hemispheres of these planets. The data indicates that Ariel is approximately one-third the size of Earth's moon and possesses a density indicative of a composite icy and rocky interior. The extensive networks of intricate extensional ridges and broad, flat-floored canyons indicate that Ariel has experienced significant geological activity historically. The activity may have been induced by interactions between Uranus's moons and tidal forces. Umbriel, comparable in size, is the darkest of the Uranian moons, reflecting merely 10% of the incident sunlight, in contrast to approximately 25% for Ariel, although some brighter, potentially newer patches of material exist in certain craters. On Umbriel, Voyager discovered solely a heavily cratered surface, lacking significant instances of more intricate geology. The discoveries of the asteroids Ceres, Pallas, Juno, and Vesta in the early 19th century initiated a new domain of solar system investigation, termed minor planet research. Nevertheless, it required over 35 years to identify any new asteroids following the discovery of Vesta in 1807. Nonetheless, enhancements in telescope sensitivity by mid-century resulted in a significant increase in the known population, and by 1857 there were 50 identified asteroids, all orbiting within what would later be termed the main asteroid belt, situated between Mars and Jupiter. The asteroid population attracted the interest of American mathematician Daniel Kirkwood. In 1846, Kirkwood achieved recognition for proposing a variant of Kepler's law relating planetary spin rates to their distance from the Sun, which initially appeared accurate. Notwithstanding the ultimate dismissal of the concept owing to superior data, Kirkwood persisted in exploring additional research on the dynamics of the solar system. Upon analyzing the orbital characteristics of approximately 50 asteroids designated in 1857, he observed a striking phenomenon. Rather than exhibiting a uniform, random, or bell-shaped distribution of distances from the Sun, the asteroids clustered at specific distances, with numerous bodies orbiting at particular intervals and none at others. Kirkwood identified that the regions in the main belt lacking asteroids correspond to areas where an object completes multiple orbits, represented as a simple integer related to Jupiter's orbit. Kirkwood discovered an absence of asteroids at 2.25 astronomical units, a region where an object would complete 3 orbits around the Sun for each orbit of Jupiter. He accurately posited that the resonance between Jupiter and objects in those regions would impart an additional gravitational influence from Jupiter, ultimately displacing them from that vicinity, or potentially expelling them from the main belt altogether. Over 150 years of data have substantiated the prediction, leading astronomers to designate these gaps in the main belt as the Kirkwood gaps in recognition of their discoverer. The gap positions are referred to as mean motion resonances. We have identified additional gaps at 5 to 2, 7 to 3, and other mean motion resonances, and within the rings of Saturn, where mean motion resonances among embedded moons create these gaps. The Sun is the most massive, energetic, and significant object in the solar system, making it unsurprising that numerous 19th century astronomers directed their advancing telescopes toward our proximate star to examine its internal mechanisms. Astronomers can measure and monitor features such as sunspots on the Sun's visible surface and the photosphere by employing appropriate filters or projecting the solar disk onto a wall or screen. Researchers have examined sunspots for centuries, and systematic observations from the early 17th century uncovered an 11-year cycle of recurring solar activity. Advancements in telescopes and observational methodologies have facilitated a more detailed study of them. Richard Carrington, an English amateur astronomer, was one of the most renowned and prolific observers of sunspots. On September 1st, 1859, Carrington noted a pronounced luminosity adjacent to a notably dense aggregation of sunspots. The event endured for merely a few minutes. The following day, however, witnessed global reports of significant auroral activity and substantial disturbances to telegraph and other electrical systems. Carrington observed the inaugural documented instance of a solar flare, an immense explosion in the sun's atmosphere capable of ejecting high-energy particles into the solar system at tremendous velocities. Solar storms are the significant impacts of this solar wind colliding with the Earth's protective magnetic field. Since then, observers have noted numerous flares and storms. However, visual documentation and ice core data indicate that the 1859 event was the inaugural and most significant in recorded history, possibly a once-in-a-millennium mega-flare. Carrington's scientific observations established a correlation between solar activity and the Earth's environment, sparking significant interest in studying space weather, the interaction of solar wind with all planets. The current fleet of Earth-orbiting satellites constitutes billions of dollars in technology and infrastructure that is particularly susceptible to disruption from solar flares and subsequent storms, especially during heightened sunspot activity. This is one reason why NASA and other space agencies are highly motivated to persist in Carrington's significant work of predicting, monitoring, and comprehending the impacts of space weather. Urbain Le Verrier, a French mathematician, was still basking in his 1846 mathematical discovery of Neptune when he undertook his subsequent theoretical endeavor. For several decades, astronomical observations of Mercury's swift orbit, which completes a revolution around the Sun in merely 88 days, uncovered discrepancies in its motion, leading to erroneous predictions of solar transits and other observational phenomena associated with the planet. Kepler's and Newton's laws of motion functioned exceptionally for the solar system's planets, moons, and asteroids, except Mercury. What transpired? Le Verrier hypothesized that Mercury's orbital irregularities mirrored those of Uranus over a decade prior. An additional planet must intermittently exert a gravitational influence on Mercury, disturbing its orbit. We awaited the discovery of another planet. Le Verrier conducted calculations and forecasted the position of the undiscovered planet. He deduced that it was likely near the Sun, possessing an orbital period of approximately 20 days. He named it Vulcan, after the Roman deity of fire. In 1859, he proclaimed his discovery to the French Academy of Sciences, and the quest for Vulcan persisted. Mercury is difficult to observe with a telescope because its persistent solar glare inhibits visibility beyond approximately 20 degrees in the sky. Furthermore, the prediction that Vulcan would never exceed a distance of 8 degrees from the Sun proved to be even more formidable. Nevertheless, both professionals and amateurs continued their search. Le Verrier investigated several accounts of minor celestial bodies crossing the Sun in approximately the correct location or objects of suitable luminosity detected during eclipses. However, subsequent observations failed to corroborate any of these claims. Le Verrier died in 1877, convinced that Vulcan had yet to be discovered. Einstein's theory of general relativity and the curvature of spacetime near the Sun ultimately elucidated Mercury's orbital behavior, leading astronomers to never discover Vulcan. Le Verrier's quest endures. Contemporary astronomers are investigating a proposed population of diminutive asteroids within Mercury's orbit, termed vulcanoids. During the latter half of the 19th century, proficient astronomers and instrument artisans, including William Lassell in England and Alvin Clark in America, conceived, produced, and utilized larger, superior telescopes. Clark was proficient in the design and fabrication of large glass refracting lenses. He amalgamated them to achieve elevated angular resolution and achromatic performance. thereby eliminating the rainbow and halo effects prevalent in earlier refractor designs with large lenses. Alvan Clark and Sons, telescope manufacturers in Massachusetts, attained global acclaim for their superior instruments, many of which remain operational today. Alvan Graham Clark, one of the Clark sons, frequently evaluated the company's new lenses during his astronomical research. On January 31, 1862, while observing from the periphery of Boston, the younger Clark directed an 18.5-inch 47-centimeter refracting telescope at the luminous proximate star Sirius. In 1844, German mathematician Friedrich Wilhelm Bessel postulated that the apparent motion alterations of the bright stars Sirius and Procyon were induced by unseen companions. The exceptionally clear night and the high-quality lenses allowed Clark to identify the faint companion to Sirius, now referred to as Sirius B. Although significantly dimmer, the spectrum of Sirius B bore a resemblance to that of Sirius by the early 20th century. We quickly identified it and several other faint stars as members of a newly classified group of small, hot stars known as white dwarfs. White dwarfs are recognized as a prevalent final stage of low-mass, sun-like stars that have exhausted their hydrogen fuel, but lack the mass to undergo supernova explosions. Through examining their orbits and applying Kepler's laws, white dwarfs such as Sirius B exhibit remarkable density, containing between 0.5 and 1.3 solar masses within a volume comparable to that of Earth, resulting in a density exceeding 1 million grams per cubic centimeter. Consequently, white dwarf stars belong to an exclusive category of compact objects encompassing neutron stars and black holes, characterized by the highest known densities in the universe. On a clear, moonless night, proceed to a dark sky site distant from urban areas, settle on a blanket or in a comfortable reclining chair, and gaze upward. After your eyes acclimate to the subdued illumination of the stars, you will quickly discern a brief, luminous streak traversing the sky. You have just observed a meteor, a small fragment of rock or ice from space entering the Earth's atmosphere and incinerating due to friction. Meteors, commonly called shooting stars, can be observed several times per hour on a typical clear night. Occasionally, typically at the same time each year, astute and fortunate observers may witness dozens or even hundreds of meteors per hour, a meteor shower. Infrequently, a tempest of thousands of meteors per hour can momentarily illuminate the night sky, producing a celestial display comparable to any New Year's Eve or Independence Day festivity. For millennia, individuals have regarded meteor showers or storms as foreboding. In the late 1860s, astronomers discovered the relationship between meteor showers and comets. The solution to the mystery was the independent discovery in 1866 in France and America of a new short-period comet, Tempel-Tuttle, named after its discoverers. Other astronomers, including the French mathematician and Neptune discoverer Urbain Le Verrier, recognized that Tempel-Tuttle's orbit closely resembled the trajectories of meteors frequently observed during the mid-November shower, known as the Leonids. This enabled astronomers to precisely forecast the subsequent significant Leonid shower, which transpired at the turn of the 20th century, thereby demonstrating that meteor showers and storms occur when the Earth traverses regions of icy and rocky debris left by a comet that previously passed through the same spatial area. Alongside the Leonids in mid-November, one can also observe the incineration of minuscule comet fragments during the Perseid shower in mid-August, originating from comet Swift-Tuttle. The Orionids in late October, from Halley's Comet. A total solar eclipse occurs when the new moon entirely obscures the sun's disk, projecting its shadow onto a limited area of the Earth, creating a remarkable and awe-inspiring phenomenon. Throughout human history, individuals regarded such occurrences as ominous signs of fear, disaster, and transformation. By the 19th century, Scientists regarded accurately predicted eclipses as significant natural experiments, opportunities to examine the Sun's atmosphere under unique conditions. On August 18, 1868, French astronomer Jules Janssen organized a specialized expedition to India to observe the solar corona's total solar eclipse and conduct spectroscopic analyses. His data uncovered a novel, unrecognized Fraunhofer-like emission line in the solar spectrum. Several months later, British astronomer Norman Lockyer devised a technique to obtain spectra of the Sun's atmosphere without requiring an eclipse, and he detected the identical new spectral line. Lockyer and Janssen designated the new element helium, derived from the Greek term for the Sun. By the end of the 19th century, scientists identified helium, He, on Earth as a gas linked to radioactive uranium deposits. They examined the novel gas comprehensively, acquiring knowledge of its remarkable properties. For instance, helium liquefies at 4 degrees Kelvin, and at temperatures near absolute zero, it transitions into a superfluid, an almost frictionless, zero viscosity substance. Over a century of experiments and observations have demonstrated that helium possesses a relatively simple and stable structure, typically characterized by a nucleus containing 2 protons and 2 neutrons, He4, though it occasionally exists with a single neutron, the isotope He3. Due to its simplicity, helium is the second most prevalent element in the universe, with the majority likely originating from the Big Bang. Helium continues to be produced today by decaying radioactive elements, including uranium. Janssen and Lockyer's diligent pursuit of the unforeseen led to the discovery of a colorless, odorless, non-toxic, inert substance that now accounts for nearly a quarter of our galaxy's observable mass. Deimos. By the mid to late 19th century, the utilization and enhancement of the telescope enabled astronomers to identify 2 additional planets and over a dozen new moons in the outer solar system. Nonetheless, the inner solar system produced only a limited number of discoveries, apart from identifying a small quantity of main belt asteroids. Asaph Hall, an American astronomer and professor at the U.S. Naval Observatory, was astonished to discover that few astronomers had endeavored to search for moons orbiting Mars. Indeed, it was a challenging issue due to the intense luminosity emanating from the red planet. However, Hall recognized his exceptional access to a superior instrument, a 26-inch, 66-centimeter Alvan Clark and Sons refractor, which was then the largest refracting telescope globally. Mars and Earth align approximately every 26 months during opposition, when Mars is positioned opposite the Sun. Hall utilized the superior opposition of 1877 and the Clark refractor's exceptional image quality to investigate the satellites of Mars. On August 11, 1877, he observed a dim object in proximity to the planet, moving in tandem with it. On subsequent nights, he confirmed that it was a moon orbiting the planet, accompanied by a second moon even nearer to Mars. A colleague proposed naming the moons after the Greek sons of Mars, Dread, Deimos, and Fear, Phobos, and the names were adopted. Hall and others concluded that Deimos is quite diminutive, but further information remained scarce until space missions to Mars commenced observations of the satellites as opportunities presented themselves. Deimos has been confirmed to be diminutive, 9.3 times 7.5 times 6 miles, 15 times 12 times 6, 10 kilometers, irregular and resembling an asteroid, characterized by a cratered yet peculiarly smooth and subdued surface texture. Astronomers hypothesize that Deimos may be a comparatively porous, rocky entity with a composition akin to certain chondritic meteorites, which constitute the foundational materials of Earth and other planets. The density is approximately 1.5 grams per cubic centimeter, and there is no indication of an icy surface. Nonetheless, A dedicated mission to Deimos may be required to ascertain whether it is a captured asteroid. Phobos. Following the initial identification of Deimos on August 11, 1877, American astronomer Asaph Hall persisted in observing the Martian skies with the 26-inch, 66-centimeter Alvan Clark and Sons refractor at the U.S. Naval Observatory in Washington. Fog and inclement weather frequently disrupted D.C. Hall's endeavors and were ultimately rewarded by his perseverance. He confirmed that Deimos orbited Mars, and on August 17th to 18th, he also observed a second faint small moon, which was subsequently named Phobos. Hall and other astronomers swiftly recognized that Phobos orbits Mars more closely than any known moon relative to its primary planet. So closely, in fact, that with an orbital period exceeding 7.5 hours, it revolves around Mars more rapidly than Mars rotates on its axis. An observer on the surface of Mars would witness Phobos rising in the west and setting in the east, despite its orbit around Mars aligning with the planet's rotation direction. The outline of Phobos as it transits the Sun, captured by the NASA Mars rover Opportunity on January 21, 2006. Contemporary space missions have elucidated additional information regarding this diminutive, somewhat reddish asteroid-like entity. However, numerous enigmas persist. Phobos measures 17 times 13.7 times 11 miles, 27 times 22 times 18 kilometers, and possesses a density of approximately 1.9 grams per cubic centimeter, indicating that it is composed of porous, rocky, chondritic material, potentially akin to that of Deimos. The surface is extensively marked by significant cratering, featuring a series of profound grooves that encircle a prominent crater, Stickney, named in honor of Hall's spouse, Angeline Stickney. Is Phobos an asteroid that Mars has captured from the adjacent main asteroid belt? Or is it a fragment of Mars formed from the debris of a colossal impact on the red planet? In 1988, the Soviets dispatched 2 robotic probes to land on Phobos. However, both were unsuccessful, one during transit and the other after merely a few months in Martian orbit. 2011, Russia initiated a new robotic mission, which failed shortly after its launch. New mission concepts are being developed. However, it appears that Phobos will persist in concealing its mysteries. 1676, Danish astronomer Ole Christensen Romer and his Dutch counterpart Christian Huygens became the first scientists to establish that light propagates at a finite velocity. Their preliminary estimate of the speed of light was somewhat underestimated. However, by the 1860s, physicists like Jean Foucault had nearly approximated the contemporary accepted value, 186,282 miles per second. Nevertheless, scientists of the 19th century remained uncertain as to whether light necessitated a medium for propagation. Isaac Newton and Aristotle posited the existence of a luminiferous ether, or simply ether, through which light particles traversed. In the late 1870s, Scottish physicist James Clerk Maxwell proposed a method for physicists to investigate the existence of ether by examining minor fluctuations in the speed of light based on the Earth's motion relative to the ether. In 1887, American physicists Albert Michelson and Edward Morley conducted a sophisticated experimental test to verify the existence of the ether based on Maxwell's theories. The Michelson-Morley experiment split a light beam into 2, employing mirrors and a small telescope to recombine the beams. Altering the distance between the mirrors may result in the beams reinforcing or canceling each other, ultimately producing a distinct interference pattern of light waves within the telescope, akin to the convergence of wave ripples on a pond. The scientists would detect a highly sensitive alteration in the fringe pattern as they rotated the apparatus, which is suspended on a pool of liquid mercury, if the speed of the light beams varied due to their interactions with the ether. Nevertheless, they noted no such alteration, thereby confirming the invariant nature of the speed of light and offering conclusive proof against the existence of luminiferous ether. The experiment laid the groundwork for significant progress in physics and astronomy during the 20th century, encompassing Einstein's relativity theories. In the latter half of the 19th century, physicists achieved significant progress in comprehending light and energy. The German physicist Gustav Kirchhoff formulated essential equations that delineate the emission of electromagnetic radiation by an idealized light-absorbing entity known as a blackbody at a specific temperature. He found that black holes emit a broad spectrum of energy at standard object temperatures, from the longer wavelengths of radio and infrared radiation to the shorter, higher energy wavelengths of visible and ultraviolet light. 1893 German physicist Wilhelm Wien formulated these concepts and established Wien's law, illustrating the inverse correlation between an object's temperature and peak energy emission wavelength. Hotter objects predominantly emit energy at shorter ultraviolet and visible wavelengths, whereas cooler objects primarily emit in the infrared spectrum. Max Planck, a German physicist, would elaborate on these concepts regarding black bodies and light, contributing to the establishment of quantum mechanics. Astronomers employed this novel comprehension of light and energy to visually analyze observable objects. Wien's law enabled astronomers to ascertain the relative temperatures of stars. Hotter stars emit a greater proportion of their energy at shorter wavelengths, resulting in a blue appearance, while cooler stars predominantly emit energy at longer wavelengths, with their spectra peaking in the yellow, orange, and red regions. Our Sun is a yellowish star, positioning it at the average to the slightly cooler end of the stellar color spectrum. Consequently, scientists in the 20th century systematically comprehended the origin, evolution, internal mechanisms, and eventual destiny of stars, utilizing their colors as essential observational criteria for classification based on temperature. The Milky Way extends from horizon to horizon, featuring luminous starry bands and dark voids resembling a celestial Jackson Pollock painting on a vast cosmic canvas. On such exquisite nights, it is evident why our ancestors revered the night sky and sought to comprehend its phenomena. In the late 19th century, numerous major cities globally were regarded as dark observing sites. But the widespread electrification of the night sky occurred only post-World War II. Consequently, the American astronomer E. Barnard seized the opportunity to relocate to the University of Chicago in 1895 to utilize the newly acquired world's largest refracting telescope, the colossal 40-inch, 102-centimeter lens at Yerkes Observatory. Equipped with a powerful telescope and his burgeoning interest in astrophotography, Barnard commenced the collection of optimal data on luminous star fields and dark, ostensibly vacant regions throughout the Milky Way's vast expanse. A significant collaborator on B, the German astronomer and astrophotographer Max Wolf, conducted studies on Barnard's Milky Way. Wolf recognized that numerous astronomers were perplexed by the dark lanes of the Milky Way, which the English astronomer William Herschel referred to as voids in the sky. Meticulous observations may uncover subtle embedded stars or distant background stars, enabling astronomers to ascertain the characteristics of the dark lanes from Barnard's photographs and Wolf's analysis. Wolf presented a compelling and ultimately precise argument. The dark regions in the Milky Way are vast clouds of relatively dense dust that obscure the otherwise brilliant light of the background stars, inhibiting their visibility. He noted that regions of luminous nebulosity, likely from newly formed stars, frequently accompanied the dark lanes. This prompted him to hypothesize that the dark regions might be cosmic cocoons, experiencing compression and densification to generate new stars. The initial hypotheses posited by Wolf and Barnard regarding the origin of the dark lanes have been validated. We frequently view Earth as a natural paradise, in contrast to the intense heat of Venus, which is nearer to the Sun, or the icy desolation of Mars, which is more distant from the Sun. By the conclusion of the 19th century, scientists recognized that Earth is a viable oceanic planet, primarily due to the impact of two relatively minor, yet critically significant atmospheric gases, water vapor, H2O, and carbon dioxide, CO2. In their absence, the oceans of Earth. In the 1820s, the French mathematician Joseph Fourier was the inaugural scientist to ascertain that Earth's equilibrium temperature, or the surface temperature resulting solely from solar heating, was significantly below freezing. What is the reason for the oceans being in a liquid state? Fourier hypothesized that the atmosphere could function as an insulator, retaining heat similarly to the glass panels of a greenhouse. However, Fourier required a solution. Swedish physicist and chemist Svante Arrhenius demonstrated that atmospheric gases elevate the surface temperature by over 30 degrees, maintaining our planet's temperature above freezing. The primary gases involved are predominantly water vapor and carbon dioxide. These transparent gases permit sunlight to penetrate the surface while absorbing a substantial fraction of the planet's emitted infrared heat energy, resulting in atmospheric warming. Fourier's preliminary concepts and experiments resulted in the term greenhouse effect, despite the warming mechanism differing from that of an enclosed glass structure. Arrhenius recognized that greenhouse warming was a straightforward and advantageous result of Earth's natural prevalence of water and carbon dioxide. He hypothesized that historical decreases in carbon dioxide specifically could account for the ice ages. He was the first to hypothesize that the future combustion of fossil fuels could increase carbon dioxide levels and contribute to global warming. The Earth's climate is more intricate than Arrhenius anticipated, yet his apprehension regarding humanity's environmental impact has proven to be prophetic. During the late 19th century, physics laboratories in Europe and America were vibrant with novel discoveries about electricity and magnetism. The recent capability to generate and store substantial voltages and currents for diverse experiments frequently resulted in unexpected discoveries, exemplified by German physicist Wilhelm Röntgen's 1895 investigation of high-voltage cathode ray tubes that produced an enigmatic new type of radiation, which he named X-rays. French physicist Henri Becquerel hypothesized that X-rays might induce phosphorescence in certain natural materials. In 1896, he performed a series of experiments to ascertain whether these materials emitted X-rays upon exposure to sunlight, inadvertently discovering that one of the materials, uranium salts, emitted radiation spontaneously. He had discovered radioactivity, a phenomenon distinct from X-rays. Becquerel subsequently collaborated with fellow French physicists Pierre Curie and Marie Skłodowska-Curie, who shared an interest in the peculiar and exotic properties of the newly discovered spontaneous radiation. Marie Curie's research on uranium resulted in the discovery of two new radioactive elements, polonium, named after her homeland of Poland, and radium. Becquerel and the Curies were awarded the 1903 Nobel Prize in Physics for their seminal discoveries. Scientists have employed radioactivity as a natural lock for the past century because of its consistent energy release and elemental decay. By utilizing the age and evolution of the Sun as a reference, scientists have employed radioactivity to precisely ascertain the ages of the Earth, Moon, meteorites, and consequently the entire solar system and beyond. Due to radioactivity and the groundbreaking contributions of scientists such as Becquerel and the Curies, we now possess remarkable accuracy in determining that the Earth is 4.54 billion years old and that the solar system originated 4.567 billion years ago. By the end of the 19th century, most astronomers acknowledged that constructing increasingly larger telescopes was not the sole method for examining progressively fainter objects. Equally significant as enhancing light-gathering capacity was augmenting the sensitivity of the detector employed to capture that light. Consequently, more observatories transitioned their preferred detectors from the human eye to photographic plates. The Harvard College Observatory, HCO, was similarly affected. Its late 19th century director, Edward Charles Pickering, innovated astrophotography to obtain and document high-resolution spectra of stars. William Henry Pickering, the brother of Pickering, was likewise an HCO astronomer. In 1899, he examined photographic plates of the sky near Saturn, captured a year prior by HCO staff member Delisle Stewart, and identified a faint new moon orbiting the planet. This moon exhibited unusual characteristics. It orbited retrogradely relative to Saturn's other moons, following a highly eccentric and inclined trajectory, situated 4 times farther from Saturn than the nearest moon, Iapetus. W. H. Pickering designated the new moon as Phoebe, adhering to the convention of naming Saturn's satellites after Titans from Greek mythology. We employed photography to identify Phoebe, the inaugural moon in our solar system, rather than relying on our unaided vision. Astronomers acquired more comprehensive data regarding Phoebe during the Voyager 2 flyby of Saturn in 1981, especially via the Cassini-Saturn orbiter mission that began in 2004. The moon is relatively large and somewhat spherical, measuring approximately 134 miles, 220 kilometers, in diameter, exhibiting low reflectivity, around 6%, and a moderately low density, 1.6 grams per cubic centimeter. Bright icy patches are observed beneath the dark surface layers on steep slopes, and spectroscopy measurements indicate that some consist of carbon dioxide ice. Phoebe's composition and unusual orbit indicate it may be a captured Centaur object, an intruder redirected from the Kuiper belt. Phoebe's influences have generated a vast, inclined, dark, and diffuse ring of icy and rocky debris surrounding Saturn. We contend that certain objects obscured the leading hemisphere of the bicolored Iapetus. What constitutes light? The inquiry has confounded philosophers and physicists for millennia. Aristotle and his adherents believed light to be a wave-like disturbance traveling through the air, whereas Democritus's followers adhered to an atomist theory, asserting that light comprised particles. Discussions regarding the wave-particle duality of light also influenced Renaissance physics. Isaac Newton posited that the behavior of light in optics could solely be elucidated by corpuscles particles, while Christian Huygens equally asserted that light must possess wave-like properties, necessitating a medium for propagation and refraction. During this perplexing period, late 19th century physicists suggested a fundamental paradigm shift in our comprehension of the essence of matter. The revolution commenced with a mathematical ruse devised by German physicist Max Planck. Planck sought to comprehend the reasons behind the radiation and energy absorption by objects at a specific temperature, such as atoms, molecules, or stars, and the occurrence of distinct bright emission lines or dark absorption lines in their spectra. At the turn of the century, Planck posited that matter could emit or absorb light, or radiation, only in discrete packets termed quanta, with their energies dependent exclusively on the light's frequency or wavelength. P. Planck's quantization of energy resulted in a comprehensive energy-level theory regarding electrons orbiting an atomic nucleus, as proposed by physicists including Niels Bohr, 1885 to 1962. In the Bohr model of atomic energy levels, the bright and dark lines in atomic spectra at varying wavelengths result from electrons acquiring and relinquishing energy between levels. The sodium atom exemplifies this. Planck regarded energy quantization as a simple mathematical postulate necessary equation, akin to the physics adage, Suppose a spherical shape. It does not inherently represent any physical reality. However, his contemporaries, including physicist Albert Einstein, discerned a profound truth in Planck's work, suggesting that light comprises energy quanta known as photons, whose interactions with matter adhere to wave-like equations. The wave-particle duality of light evolved into a foundational principle of a new field of physics known as quantum mechanics. Pickering's Harvard computers astronomers, akin to other scientists, prefer to categorize the celestial objects they examine into organized classifications, facilitating the comparison and analysis of their characteristics and histories. Establishing an effective classification system for stars was especially crucial, as thousands are observable to the naked eye, and millions can be detected through telescopes. The initial star catalogues by Hipparchus, Ptolemy, and Alsoph documented the relative brightness of prominent stars, and occasionally their color variations, ranging from blue to red. Father Angelo Secchi, an Italian astronomer, obtained spectroscopic data for thousands of stars in the 1860s, establishing the inaugural stellar classification system and categorizing them into 5 primary classes based on spectral characteristics. Numerous astronomers, notably Harvard College Observatory Director Edward Charles Pickering, endeavored to enhance and expand Secchi's classification system to categorize millions of additional stars. Pickering utilized superior telescopes for his initiative and, akin to other observatory directors of the era, employed human computers to assist in sifting through and analyzing the vast data set comprising thousands of photographic plates. Many of these computers were women employed for minimal or no remuneration to undertake tasks that many male supervisors deemed menial and monotonous, specifically measuring stellar spectral lines. Some women developed considerable expertise in stellar spectroscopy and contributed significantly. Among the most notable was Annie Jump Cannon, who utilized her understanding of absorption line strengths to reorganize and streamline what had become an overly intricate and competing classification system. Astronomers continued to utilize Cannon's 1901 classification nomenclature OBAFGKM, which spans from bluer and weaker to redder and stronger lines. Later research would reveal a direct correlation between her classifications, stellar temperature, and stellar evolution. The discovery of Phoebe in 1898 illustrates that astronomers were examining increasingly vast regions of space surrounding giant planets to identify new moons. In the 19th century, astronomers Gerard Roche and George William Hill built upon Joseph Louis Lagrange's work in celestial mechanics to derive more precise calculations regarding the maximum distance a moon can maintain from a planet while remaining in a stable orbit, a region now referred to as the planet's Hill sphere. In 1904, astronomer Charles Perrine of Lick Observatory identified Jupiter's dim, remote outer moon, orbiting at a distance 4 times greater than that of Callisto, the farthest Galilean satellite. It was referred to as Jupiter 6 until 1975, was officially named Himalaya, after the Greek nymph who bore 3 sons of Zeus. During its journey to Saturn, the Cassini mission captured remote images of Himalaya, indicating its diameter to be approximately 93 miles, 150 kilometers. Subsequently, researchers identified Himalaya as the largest and most luminous among over 50 small, irregular satellites orbiting Jupiter at considerable distances. Nevertheless, Jupiter is not the sole planet with irregular satellites. Saturn possesses 38, Uranus has 9, and Neptune has 6. Numerous irregular moons exhibit retrograde orbits about the principal moons of the giant planets, and many possess significantly inclined trajectories concerning their primary planet's equator. In contrast to the principal moons and Earth's moon, none appear to be tidally locked, consistently presenting one face toward the primary planet. These attributes lead astronomers to hypothesize that outer irregular satellites such as Himalaya are captured entities. They may have originated in proximity but drifted sufficiently close to becoming gravitationally ensnared within a giant planet's Hill sphere. They could have been main belt asteroids or gravitationally redirected and captured Kuiper belt objects. Targeted space missions may be necessary to investigate these diminutive worlds further. Einstein's miracle ear envisions the experience of acquiring knowledge regarding the universe, space, and time that remains unknown to others. Consider the frustration of being ahead of one's era, coupled with the challenge of communicating such groundbreaking insights to an audience that neither comprehends nor believes them. Would the profound exasperation of this predicament eclipse the unparalleled exhilaration of achieving one of science's paramount discoveries? Albert Einstein, the eminent physicist and visionary, confronted this quandary. Born in Germany to middle-class parents, Einstein exhibited an early proficiency in mathematics and physics, unconventional thinking, and conflicts with authority figures. Following his graduation from a Swiss institution with a degree in physics, he struggled to secure a teaching position. Consequently, in 1902, he commenced employment at the Patent Office in Bern, focusing on electromagnetics while patently engaging in physics pursuits. Einstein conducted extensive experiments and made significant discoveries in 1955. He elucidated the particle nature of light and the photoelectric effect, which is foundational to modern digital camera CCD charge-coupled device detectors. He also clarified Brownian motion, the random movements of molecules, formulated the theory of special relativity, asserting the constancy of the speed of light and the peculiar alterations of space and time at relativistic speeds, and crucially, demonstrated the intrinsic connection between energy and mass through the renowned equation E equals mc squared, a transformative concept that catalyzed the nuclear era. This prolific generation of ideas and insights culminated in a PhD from the University of Zurich and a Nobel Prize, acknowledging his intellectual brilliance. Einstein perpetually advanced new concepts and expanded upon his earlier theories throughout his lifetime. One of his most renowned later theories was general relativity, which elucidated gravity as a modification in the configuration of the conventional four-dimensional space-time continuum. For more than a century, astronomers and physicists have been evaluating and expanding upon Einstein's theories of relativity and other concepts, the vast majority of which have been validated. The introduction of photography in astronomy facilitated the identification of faint celestial bodies, as photographic plates possess greater sensitivity than the human eye. Rapidly moving objects such as asteroids traverse the sky at a distinct velocity compared to stars. A German astronomer, Max Wolf, was a prominent figure in late 19th and early 20th century astrophotography. Throughout his career, Wolf discovered almost 250 asteroids using his photographic methods. On February 22, 1906, Wolf made one of his most significant discoveries when he identified the 588th known minor planet. Unlike most others, however, this one was far beyond the main asteroid belt, with an average distance from the Sun of around 5.2 astronomical units, almost the same as Jupiter. The Austrian astronomer Johann Palisa, also a prolific discoverer of asteroids, found that Wolf's discovered object was orbiting the Sun in approximately the same orbit as Jupiter, but about 60 degrees ahead. The French mathematician Joseph-Louis Lagrange proposed the idea of gravitationally balanced stability regions, or Lagrange points, in 1772, and it became clear that Wolf had verified it after finding more asteroids in the same area and a corresponding area some 60 degrees behind Jupiter. Wolf discovered the first of Palisa's Trojan asteroids, named after the Trojan War heroes. Wolf's asteroid number 588, which orbits near the L4 Lagrange point of the Jupiter-Sun system, was eventually named Achilles after the Greek hero from Homer's Iliad. Other warriors from the Greek camp named other asteroids in the L4 region, while heroes from the Trojan camp named those in the L5 region. Astronomers have identified over 4,000 Trojans within the two camps and estimate that Jupiter Trojan's L4 and L5 clouds could harbor up to 1 million asteroids exceeding 0.6 miles 1 kilometer in diameter. Many of these bodies are dark and reddish, resembling inactive comets, yet little additional information is available regarding this vast population of small celestial objects. This is a graphical depiction of the locations of 4,079 Jupiter-Trojan asteroids, yellow dots, with established orbits as of 2011. The leading L4 cloud of Reeks is positioned at the top, while the trailing L5 Trojans are located at the lower right. Jupiter is situated at the center right. The plot was generated using the Celestia Planetarium software. During the 1877 opposition, an excellent and relatively rare closer-than-normal alignment between Earth and Mars partially discovered the Martian moons Phobos and Deimos. Others took advantage of the opportunity to focus on Mars itself, including Italian astronomer Giovanni Schiaparelli, who created numerous maps in which he gave the planet seas, darker areas, and continents, bright areas, historical Latin and Mediterranean names. He also observed fine, dark, linear features on the planet that he thought might be channels of some kind. Many people often mistranslated the Italian word for channels, canali, into English as canals. Percival Lowell, a Massachusetts industrialist, author, and astronomy enthusiast, became enthralled with Schiaparelli's and other descriptions of such linear features on Mars. Convinced that higher quality observations could reveal the features in more detail, 894, he used part of his family fortune to found a high-altitude observatory in Flagstaff, Arizona, and to equip it with a 24-inch, 61-centimeter Alvan Clark and Sons refracting telescope. Lowell Observatory quickly became one of the world's premier centers for astronomical research, and Lowell focused much of his own observing time on detailed observations and drawings of Mars. Lowell observed complex networks of dark, linear markings traversing Mars, markings that could only be attributed to an intelligent civilization. In his renowned 1906 publication, Mars and Its Canals, he theorized that these represented extraterrestrial waterways intended to transport meltwater from the polar caps to the extensive equatorial cities of the Red Planet. He propagated that a race of exceptionally adept engineers resided on Mars. Contemporary photography and space missions have demonstrated that Schiaparelli and Lowell's observations were probably optical illusions. Nevertheless, the public and scientists remain intrigued by Mars as a possible habitat for life. On June 30, 1908, a remarkable occurrence startled numerous inhabitants of the Krasnoyarsk Krai region in central Siberia, near the Tunguska River. At approximately 7:15 a.m., the skies above Siberia ignited with a blinding flash of light, followed by resounding explosions. The ground trembled with the intensity of a magnitude 5.0 earthquake. A scorching wind and a rain of fire devastated and uprooted 80 million trees across over 811 square miles, 2,100 square kilometers, an expanse half the size of Rhode Island. Seismic shock waves from the event were detected in Asia and Europe, and the night skies globally emitted an unusual luminescence for several days thereafter. Scientists hypothesized that the inhabitants of Tunguska had encountered a meteoroid impact. The initial scientific expedition to explore the isolated, uninhabited area did not occur until 1927, when Russian mineralogist Kulik endeavored to locate the impact crater and possible iron-nickel meteorite deposits, albeit without success. The airburst explosion primarily inflicted surface damage through shock waves, heat, and fire, yet no corresponding crater was created. For over a century, planetary scientists have contested the nature of the impactor, with some asserting it was an icy comet fragment that disintegrated catastrophically upon atmospheric entry. In contrast, others argue it was a small, rocky asteroid, potentially a rubble pile object too fragile to endure on the surface. Regardless of its origin, an object approximately 33 feet, 10 meters, in diameter, traveling at roughly 6 miles, 10 kilometers per second, detonated around 6 miles, 10 kilometers above the surface with an energy equivalent to about 10 megatons of TNT, approximately 1,000 times the explosive yield of a World War II atomic bomb. Notably, the Tunguska explosion resulted in no fatalities. Tunguska exemplifies the critical need to understand impact events, especially the catastrophic effects that even minor objects traveling at high velocities can impose on our environment during rare collisions with Earth. Astronomers have long recognized that determining the distances to the nearest stars is feasible through their parallax shift, resulting from Earth's annual motion around the Sun. Nevertheless, despite utilizing the world's largest telescopes, how can we ascertain the distances to more distant stars that exhibit no detectable parallax? The discovery originated from Henrietta Swan Leavitt, a member of Harvard College Observatory Director Edward Pickering's Harvard Computers, who was responsible for analyzing millions of stars across thousands of photographic plates. Leavitt focused on the brightness fluctuations in periodic or pulsating variable stars. She scrutinized thousands of variables and identified a compelling pattern among a specific category known as Cepheid variables, named after the prototype Delta Cephei. In 1908, she published her initial observation that the greater the luminosity of a Cepheid, the longer its period. This period-luminosity relationship indicated that Cepheids with identical periods that exhibit brightness variations must be at different distances from. By independently determining the distance to any Cepheid, we could utilize them as yardsticks or standard candles. In 1913, Danish astronomer Einar Hertzsprung independently calculated the distances to various Cepheid variables through precise parallax measurements, which were instrumental in estimating distances to other Cepheids. Regrettably, Leavitt's largely unrecognized discovery and subsequent examination of Cepheids in the Andromeda Galaxy and other locations demonstrated that Andromeda and similar nebulae were, in fact, distinct galaxies located millions of light-years away from the Milky Way. In the early 20th century, astronomers globally cataloged and classified vast numbers of stars based on their colors and spectral lines, building upon the methodologies established by Edward Pickering's team at Harvard. Two astronomers, Einar Hertzsprung from Denmark and Henry Norris Russell from the United States, significantly advanced by plotting stars' spectral classes or temperatures against their intrinsic brightness, accounting for their distances from Earth. They organized the majority of stars into a broad sequence from the upper left to the lower right. Hertzsprung introduced the term in sequence to describe this notable trend among the stars. By around 1910, these plots, known as Hertzsprung-Russell (HR) diagrams, began to be utilized. In subsequent decades, astronomers recognized that the main sequence was not merely a random aggregation. It constituted an evolutionary trajectory for assessing stars' age and ultimate destiny. Most stars originate when their central pressures and temperatures reach sufficient levels for the nuclear fusion of hydrogen into helium. During this hydrogen-fusing phase, a typical star occupies a position on the main sequence determined by its mass, with luminous stars several to 10 times the mass of the Sun, blue giants, located at the upper left of the diagram, and dim stars ranging from 1/10 to 1/2 the Sun's mass, red dwarfs, positioned at the lower right. As stars age and deplete their hydrogen reserves, they deviate from the main sequence and ultimately display distinctive, often dramatic behaviors, again contingent upon their mass. Astrophysicists like Arthur Eddington and Hans Bethe elucidated the intricacies of stellar interiors, enabling predictions regarding the life cycles of stars with particular masses. Our Sun is classified as an average mass, middle-aged main sequence star, which is projected to expand into a red giant in approximately 5 billion years, shed its outer layers into a planetary nebula, and ultimately diminish into a white dwarf. In the decade following Cepheid 1908, astronomers recognized variable stars as effective tools for measuring cosmic distances. They endeavored to ascertain distances to spiral nebulae, globular clusters, and other mysterious entities to establish their position relative to the Milky Way. The dimensions of the Milky Way itself were fiercely contested, with numerous astronomers positing that it constituted the entirety of the universe. Conversely, the 18th century philosopher Immanuel Kant referred to the remote nebulae as one of many separate island universes. The inaugural astronomer to conduct an experimental assessment of the Milky Way's dimensions was American astronomer Harlow Shapley, who examined the distribution of globular clusters in the celestial sphere. Shapley employed Cepheid variable stars to ascertain the distance to a proximate globular cluster, presuming uniformity in size, and utilizing the fluctuating apparent diameters of other clusters to gauge their distances. By 1918, he concluded that the globular clusters constitute a halo encircling the flat disk of our galaxy, allowing him to estimate that the Milky Way spans approximately 300,000 light-years, with the Sun positioned not at the center but approximately 50,000 light-years offset, thus challenging heliocentrism. This revelation was significantly larger than previously believed, leading Shapley to dismiss the existence of island universes. The globular clusters and spiral nebulae must be adjacent to or within the Milky Way. Shapley's estimation of the Milky Way's size was approximately threefold excessive, primarily due to his erroneous assumption that all globular clusters possess uniform dimensions. The galaxy's disk spans roughly 100,000 light-years in diameter and is about 1,000 light-years in thickness, with a relatively thicker central bulge. The Sun is around 7,000 light-years from the galactic center. While Shapley accurately identified globular clusters within and surrounding the Milky Way's diffuse halo, he misjudged the nature of spiral nebulae. Subsequent research by Edwin Hubble and others revealed that spirals and various other types of nebulae are distinct galaxies, some akin to our own and others dissimilar, all situated millions to billions of light-years away. Centaur asteroids. Despite discovering nearly 1,000 asteroids in the early 20th century, astronomers continued encountering unexpected, mysterious objects. A notable instance is the discovery of asteroid 944 by German astronomer Walter Baade in 1920. This asteroid, later named Hidalgo in honor of the Mexican priest and independence leader Miguel Hidalgo, exhibited a highly comet-like tilted and eccentric orbit, eccentricity of 0.66. Ranging from the inner edge of the main asteroid belt, 1.95 astronomical units, or AU, to a distance nearly equivalent to that of Saturn from the Sun, 9.5 AU. In 1977, scientists identified the asteroid 2060 Chiron, which traverses a comet-like orbit between Saturn and Uranus. Subsequently, researchers have uncovered several hundred additional eccentric asteroids with orbits predominantly between Jupiter and Neptune. This hybrid population of part asteroid, part comet entities is designated as centaurs, drawing inspiration from mythical beings that are half horse and half human. The varied hues of centaurs reflect their composition of multiple substances. Certain telescopic spectra reveal that they consist of tholins, organic byproducts resulting from the ultraviolet radiation of methane or ethane ice, water ice, and methanol ice. Numerous components are also found in comets. Scientists have detected a faint coma, a nebulous comet-like head, in 3 centaurs, including Chiron, suggesting cometary activity. Centaurs have not yet been observed by spacecraft. However, numerous astronomers hypothesize that Saturn's irregular moon Phoebe could be a captured centaur, offering a detailed perspective on their characteristics. Considering their trajectory through the orbits of the giant planets and their limited lifespan of merely a few million years before transitioning to new orbits, we must accelerate our research efforts. Although astronomers classified stars according to attributes like color, temperature, and intrinsic luminosity, understanding the mechanisms of stellar function took considerably longer. What causes their luminosity? What is the source of their energy? What processes occur within a star? Arthur Stanley Eddington, a British astrophysicist, was pivotal in addressing these inquiries. Eddington sought to comprehend the gravitational collapse of nebular gas and dust in the formation of a star. Astronomers recognized that gravity was the force drawing the gas into a spherical shape and inducing compression. However, the question remained: what prevented gravity from compressing stars into increasingly smaller dimensions? In 1924, Eddington published a comprehensive model elucidating how the extreme temperatures and pressures within a star generate radiation pressure, an outward force that counteracts gravity and enables stars to attain their equilibrium sizes. Eddington's stellar interior models enabled him to establish a straightforward correlation between a main sequence star's luminosity and its mass. A star exhibiting double the brightness of another will possess a mass exceeding 10 times that of the latter, specifically LOCM 3.5. Consequently, based on his findings, it is feasible to estimate a star's mass solely by assessing its apparent brightness and distance, allowing astronomers to demonstrate that the main sequence serves as the mass-dependent lifeline, an evolutionary trajectory followed by approximately 90% of all stars. At that time, Eddington and others comprehended the mechanics of the mass-luminosity relationship and the production of radiation pressure within a star. A prominent theory posits that gravitational contraction generates energy. Eddington posited that nuclear fusion could produce the necessary energy. However, this notion faced skepticism until the late 1930s. In August 2010, the NASA Solar Dynamics Observatory captured this remarkable ultraviolet image of a dark coronal hole in the Sun's atmosphere. This region is where solar wind particles emanate into space, producing auroral phenomena in our atmosphere. Rockets, powered by the combustion of gunpowder, have existed for over a millennium. Some assert that the Chinese originated rockets for warfare and pyrotechnics. In 1903, Russian mathematician Konstantin Tsiolkovsky authored the inaugural scholarly work that conceptualized them not merely as weapons, but also as a prospective method for space travel. He developed significant aspects of rocketry theory and advocated using liquid fuels over gunpowder to enhance combustion efficiency and improve the rocket's thrust-to-weight ratio. Tsiolkovsky is regarded as the progenitor of contemporary rocketry in Russia and the Soviet Union. Robert Goddard, an American rocket scientist and physics professor at Clark University, was the first to empirically test Tsiolkovsky's theories as well as his own, demonstrating that liquid-fueled rockets were viable and capable of generating the thrust necessary to elevate substantial masses to considerable altitudes. He developed and patented essential designs for rockets powered by gasoline and liquid nitrous oxide and the concept of multi-stage rockets, claiming their capacity to reach extreme altitudes. Although the flights of his rockets were modest by contemporary standards, Goddard's methodologies were robust, allowing others, including a cohort of post-war space race engineers led by rocketry innovator Wernher von Braun, to build upon his designs, facilitating longer, higher, and ultimately orbital and beyond launches. Similar to numerous inventors, Goddard was a visionary. He frequently operated independently and perceived opportunities that others disregarded. He was an early proponent of rocketry for atmospheric scientific experiments and, akin to Tsiolkovsky, for prospective space travel. Ironically, Warfare served as the catalyst for the subsequent advancement of rockets that would fulfill humanity's aspiration for space exploration. Robert Goddard stands beside his inaugural liquid-fueled rocket, which was launched from Auburn, Massachusetts on March 16, 1926. In contrast to contemporary rockets, this model featured its combustion chamber, nozzle, and fuel tank positioned at the apex. It ascended for 2.5 seconds and reached a height of 41 feet, 12.5 meters. In 1918, American astronomer Harlow Shapley derived the inaugural quantitative estimate of the Milky Way galaxy's dimensions by assessing the distances and orientations of the halo of globular clusters encircling the galaxy's disk. Shapley's research enabled him to approximate the location of the galaxy's center, which he identified in the brightest region of the Milky Way's prominent band of stars towards the constellation Sagittarius. As it became evident that our galaxy, alongside others meticulously examined through astrophotography and spectroscopy, is a spiral galaxy, certain astronomers discovered that stars in the Milky Way may be orbiting a shared galactic gravitational center. This is probably true for other spiral galaxies as well. Bertil Lindblad, a Swedish astronomer of the 1920s, was the inaugural researcher to examine this hypothesis comprehensively. In 1927, Dutch astronomer Jan Oort meticulously quantified the trajectories of numerous individual stars, thereby furnishing the inaugural observational evidence for Lindblad's hypothesis. He verified that the Milky Way exhibits rotation and that this rotation is differential. Specifically, stars situated at varying distances from the rotation axis orbit the center at disparate velocities, with more distant stars trailing behind those that are closer. Approximately midway from the galactic center, the Sun requires around 250 million years to complete an orbit around the galaxy's nucleus. Shapley's prior assessment indicated that the contributions of Oort and Lindblad enhanced the precision of the galaxy's rotational center. In the late 19th century, the shadowy corridors of dusty nebulosity that E. Barnard and Max Wolf examined the obscured galactic center, complicating visual observations for astronomers seeking further knowledge. Subsequently, astronomers employed X-ray, infrared, and radio telescopes to meticulously examine this region. It was ultimately discovered that the core of our galaxy contains Sagittarius A star, pronounced Sagittarius A star, a substantial energy source likely fueled by a black hole with a mass equivalent to the 1848 discovery of the Doppler shift of light equipped astronomers with a method to ascertain the velocity of celestial objects on Earth. The sole requirement was the capability to identify and quantify the displacement of an appropriate absorption line or lines through spectroscopy. In 1912, astronomer Vesto Slipher of the Lowell Observatory acquired the inaugural spectra of spiral nebulae and other entities subsequently identified as distinct galaxies. Vesto Slipher determined that the majority of spiral nebulae exhibit spectral lines that are Doppler shifted toward longer, redder wavelengths, signifying their recession from Earth. American astronomer Edwin Hubble, who also focused on spiral nebulae, began his studies in 1919 utilizing the newly available 100-inch, 254-centimeter Hooker reflector at the Mount Wilson Observatory in Southern California, which was then the largest and most sensitive telescope globally. He analyzed Slipher's galaxy redshift data and dedicated 10 years to meticulously gathering additional data independently. In 1929, Hubble released a seminal paper detailing his preliminary findings. He discovered that, notably, the redshift of galaxies escalates with increasing distance from Earth. All objects appeared to be receding from us, with the most distant ones moving quickly. The observation known as Hubble's law indicates that the observable universe's volume is expanding. This remarkable outcome aligned with prior theoretical predictions regarding the expansion of space-time by Russian cosmologist Alexander Friedmann, founded on Albert Einstein's theory of general relativity. Hubble's law posits that the universe was more compact in the past. Cosmologists currently interpret the data to suggest that the entirety of space and time, the universe as we understand it, originated from a colossal explosion known as the Big Bang, approximately 13.7 billion years ago. The Hubble Space Telescope significantly transformed our comprehension of the universe. The Hubble Space Telescope, named after the discoverer of the expanding universe, captured this exceptionally sensitive photograph in 2004 following over 11 days of exposure on a minuscule section of the sky. Nearly every point and blemish in this image represents a galaxy. The calculations of French mathematician Urbain Le Verrier regarding the probable location of a planetary mass object affecting Uranus's orbit facilitated the discovery of Neptune in 1846. Subsequent observations of Uranus and Neptune prompted certain astronomers to hypothesize that Neptune may not be entirely accountable for the anomalies in Uranus's orbit, indicating the potential existence of an Earth-sized planet concealed in the far reaches. Percival Lowell, a New England entrepreneur who established Lowell Observatory in Flagstaff, Arizona, in 1894, was one of the astronomers advocating for the existence of Planet X. Alongside American astronomer William Henry Pickering, they posited predictions regarding the probable location of Planet X. Flagstaff undertook an unproductive search from 1909 until Lowell's demise in 1916, during which a dispute over Lowell's estate temporarily halted the investigation. Pickering's search in 1919 was also unsuccessful. In 1929, the investigation recommenced in Flagstaff under the direction of 23-year-old Clyde Tombaugh, a recent addition to the staff who had garnered the admiration of Lowell Observatory director Vesto Slipher through his observations and sketches from his upbringing in Kansas. Tombaugh utilized Lowell's 13-inch, 33-centimeter astrograph, a telescope engineered for large photographic plates, to examine the anticipated areas of the sky for objects exhibiting the appropriate trans-Neptunian velocity. After nearly a year of endeavor, on February 18, 1930, he discovered a diminutive new world in the appropriate location. A British girl triumphed in a subsequent naming contest, choosing Pluto, named after the Roman deity of the underworld. A contemporary reanalysis of Uranus's orbit revealed no inconsistencies beyond Neptune's elucidation. Tombaugh's identification of Planet X resulted from expertise and serendipity. For over 75 years, Pluto was classified as the 9th planet of the solar system, orbiting at nearly 40 astronomical units. It is currently recognized to possess 5 moons, one of which, Charon, is relatively large. In the 1990s, it became evident that Pluto is merely one of the largest of the diminutive icy bodies in the Kuiper Belt. In 2006, Pluto controversially and abruptly lost its designation as a dwarf planet. Arecibo Radio Telescope. Astronomers have recognized since the early 17th century, when Galileo and others employed the first astronomical telescopes, that enhancing a telescope's sensitivity and resolution requires an increase in size. Nonetheless, physical constraints on material strengths and the capacity to grind and polish substantial glass lenses or silvered mirrors render it technically unfeasible to construct functional single-lens telescopes exceeding approximately 3 feet, 1 meter, in diameter, or single-mirror telescopes surpassing about 16 feet, 5 meters in diameter. In radio astronomy, mirrors that reflect or transmit radio waves can be constructed from metal, similar to antennas. This permits considerably larger dimensions. During the late 1950s and early 1960s, a cohort of radio astronomers and atmospheric scientists at Cornell University recognized the feasibility of constructing a large stationary radio telescope using wire mesh within natural bowl-shaped depressions. They located an appropriately radio-quiet mountains near Arecibo, Puerto Rico. Its proximity to the equator facilitates a comprehensive view of the sky. In 1960, aided by the Advanced Research Projects Agency, the U.S. military's counterpart to NASA, the construction of the vast semi-spherical dish and its supporting structures for adjustable radio transmitters and receivers commenced. The Arecibo radio telescope commenced operations in the autumn of 1963 and continues to be the largest single-dish telescope globally. The Arecibo Observatory has produced many important astronomical discoveries. Initially, during the telescope's operation, radar observations disclosed Mercury's rotational velocity and the topography of the cloud-enshrouded surface of Venus. Arecibo astronomers identified one of the earliest known pulsars, rapidly rotating neutron stars, within the core of the Crab Nebula, as well as the first millisecond pulsar, which spins at a rate of 500 to 1,000 rotations per second. Arecibo astronomers transmitted the initial radar waves to near-Earth asteroids to ascertain their dimensions and morphology, and the telescope remains the foremost observatory on Earth for calculating the trajectories of potentially hazardous asteroids that may pose an impact risk to our planet. Quasars. Like optical astronomers utilizing visible light wavelengths, early radio astronomers were eager to explore the heavens with their newly developed radio telescopes to detect the most captivating natural sources of radio waves. Alongside prominent radio sources with clearly identified optical counterparts, such as the Milky Way galaxy's center or the Crab Nebula supernova remnant from 1054, astronomers in the 1950s commenced the discovery of numerous strong radio sources lacking corresponding optical counterparts. Numerous objects appeared diminutive in the sky, resembling stars, yet were not stars. Astronomers designated them as quasi-stellar objects, abbreviated as quasars. In 1962, the most luminous quasar, designated 3C273, traversed the Moon's limb several times, enabling radio astronomers to accurately ascertain its position. Martin Schmidt, a Dutch-American astronomer, utilized this high-precision locational data to search for and optically identify the quasar using the 200-inch 5-meter Hale telescope at Mount Palomar, which had been the world's largest reflecting telescope since its inception in 1948. Upon examining the spectrum of 3C273, Schmidt observed that it differed from that of a star. Instead, it exhibited Doppler-shifted emission lines from hydrogen, indicating that it was extremely distant by Hubble's law and comprised of ionized gas traveling at approximately 16% of the speed of light. Since then, researchers have determined that quasars are the most luminous entities in the observable universe. Quasar 3C273 is among the nearest to Earth, yet it remains 2.4 billion light-years distant. This indicates that quasars are primordial entities more prevalent in the universe's formative epochs. Astronomers assert that quasars represent the tumultuous inner regions of primordial active galactic nuclei, where matter accretes into central black holes of quasar-host galaxies, emitting vast quantities of gravitational energy. A spiraling disk of matter may occasionally emit energy as intense radiation jets perpendicular to the disk. The most luminous quasars direct their energy jets almost directly at us. Cosmic microwave background radiation. Numerous cosmologists utilized Edwin Hubble's 1929 revelation of the universe's expansion as substantiation that the universe was more compact in the past. They posited that if one could traverse sufficiently back in time, approximately 13.7 billion years ago, according to recent estimates, one would ascertain that the universe originated from a Big Bang emanating from an exceedingly hot, dense, and minuscule point. Nevertheless, not all astronomers initially accepted the Big Bang theory. In 1948, an alternative model emerged, suggesting that despite the expansion of space, the continuous creation of new matter, primarily hydrogen, preserved density, the quantity of matter per unit volume, over time. The steady-state theory posits a universe without a beginning or an end, and, despite its peculiarities, it aligned with the astronomical data available at that time. Cosmologists have developed techniques to evaluate the correlation between the Big Bang and steady-state models of the universe. The Big Bang model posits that the universe should retain a subtle luminosity characterized by a distinct pattern from the early recombination era, when electrons became less ionized and space became transparent to photons. Predictions indicate that the temperature of that glow would be approximately 3 to 5 kelvins, slightly above absolute zero. This anticipated quantity or pattern was incongruent with the background radiation of the steady-state model. Radio astronomers recognized that the radiation signal would be most discernible in the microwave spectrum, particularly at 1 to 2 millimeters, and they were diligently pursuing its detection. In 1964, astronomers Arno Penzias and Robert Wilson triumphed by detecting anomalous and nearly uniform background radiation with a temperature approximating 3.5 kelvins. They were awarded the 1978 Nobel Prize in Physics for their discovery at Bell Labs, where Karl Jansky pioneered radio astronomy in 1931. Recent satellite measurements have determined that the cosmic microwave background has a temperature of 2.725 kelvins. It exhibits minor fluctuations in matter and space that seem to serve as the seeds for the eventual formation of stars and galaxies. Singularities. Despite being some of the most peculiar, exotic, and potentially misinterpreted entities, black holes can be succinctly described as collapsed stars. Their enigmatic allure arises from their inherently unobservable characteristics, and our understanding is derived solely from observing the peculiar and exquisite ways they alter and engage with their environment. When a sufficiently massive star, approximately 5 to 10 times the mass of our Sun, exhausts its hydrogen and converts it into helium and heavier elements, nuclear fusion reactions cease to counteract gravitational forces, resulting in the star's collapse. The collapse ultimately results in a colossal supernova explosion, expelling a significant portion of the star's material into space. Nonetheless, a portion of that explosive energy further compresses the dense residual core of the star, which persists in contracting, increasing in density, and emitting more energy. If the mass of the collapsed star increases, potentially by acquiring material from a companion star, there will come a time when not even light can escape the object's gravitational pull. The area surrounding the core would appear as a black hole from an external perspective. In 1965, British astrophysicist Roger Penrose mathematically demonstrated that collapsing stars can generate black holes and that massive stars ultimately contract to an infinitely small point referred to as a singularity. This is an extraordinary discovery. However, as gravity diminishes with increasing distance from the object, specifically beyond the event horizon, any light or radiation associated with the black hole can escape and be detected. The black hole's immense gravitational and magnetic fields propel gas or dust to high velocities, producing a significant portion of the observed radiation. These regions are thought to constitute quasars. Einstein's theory of relativity forecasts various peculiar phenomena at a black hole's event horizon, including the perception of time halting when observed externally. Regrettably, as information cannot escape from a black hole, it may be impossible to accurately ascertain their characteristics. Hawking's extreme physics. Research conducted by astronomers in the early to mid-20th century resulted in a comprehensive understanding of stellar mechanics and the acknowledgement of their finite lifespans. Stars are formed, undergo a typical life cycle, and subsequently perish, with the specifics largely contingent upon their mass. The most massive stars undergo supernova explosions, resulting in highly dense stellar remnants that may evolve into neutron stars, pulsars, or, if sufficiently massive, black holes. Many astrophysicists seek to comprehend these compact, high-energy entities as they and their surroundings offer opportunities to investigate some of the most extreme physical phenomena in the universe. One of the most prominent researchers is British cosmologist Stephen W. Hawking, who commenced publishing black hole physics papers as a Cambridge graduate student in 1965. He has also conducted significant research in refining theories of quantum gravity, wormholes, and the Big Bang. Hawking was especially focused on examining singularities, the infinitely small and dense remnants of the catastrophic collapse of massive stellar cores. He and his Cambridge associate Roger Penrose each made significant discoveries regarding these peculiar entities, which, due to their exceptionally high gravitational and magnetic fields, served as exemplary sites for examining Einstein's theory of general relativity and extreme instances of quantum mechanics. Hawking's theoretical research has established that singularities are feasible and potentially numerous in the universe, ranging from quasar-host galaxies to individual black hole stellar remnants. Hawking indicated that the Big Bang originated as a singularity. Thus, examining the origin and characteristics of singularities yields insights into the fundamental origins of our universe. At 21, Hawking was diagnosed with a motor neuron disease linked to amyotrophic lateral sclerosis, ALS, resulting in paralysis and reliance on a computer for communication. Despite an initially grim prognosis, he persisted and emerged as a prominent theoretical physicist, a motivational best-selling author, and a fervent proponent of scientific education and literacy for the general populace. Venera 3 arrives at Venus. The majority of media coverage regarding the 1960s space race between the United States and the Soviet Union concentrated on the human spaceflight initiative and the endeavor to achieve the inaugural lunar landing by astronauts. However, the competition also spanned a greater distance throughout the solar system. After the achievements of the Luna 3 and Zond 3 lunar orbiters, along with the Ranger 7, 8, and 9 lunar impact probes from 1959 to 1965, both the Soviet Union and the United States shifted their focus towards robotic missions aimed at investigating the proximate planets, Venus and Mars. Venus, Earth, and Mars constitute a triad of predominantly analogous terrestrial planets that, upon meticulous examination, disclose significant disparities in surface characteristics and climatic development. Telescopic observations indicated that clouds perpetually obscure Venus's surface, with only radar observations from the Arecibo radio telescope in the early 1960s disclosing certain surface details. In 1962, Mariner 2 became the inaugural probe to traverse Venus. However, significant uncertainties persisted regarding the planet's surface temperature and atmospheric pressure. The Russians commenced the Venera robotic probe program to conduct an in-depth study of Venus through a series of flybys, orbiters, atmospheric probes, and landers. The Venera 1, 1961, and Venera 2, 1965. Venus flyby missions failed before reaching the planet. However, the Venera 3 mission successfully arrived at the planet and entered its atmosphere before losing radio contact with Earth. Although the Venera 3 mission did not yield any scientific data, it is historically significant as it was the first human artifact to impact Venus on March 1, 1966. The Soviet space program's persistence yielded results. The subsequent missions of Venera 4, 5, and 6 from 1967 to 1969 were successful, with Venera 4 delivering the inaugural direct measurements of the atmospheric chemistry, temperature, and pressure of another planet, while Venera 5 and 6 contributed additional data on wind speeds, temperature, and pressure. The missions and the successful 1967 U.S. Mariner 5 flyby disclosed that Venus is an inhospitable planet, exhibiting surface pressure exceeding 90 times that of Earth and surface temperatures surpassing 840 degrees Fahrenheit, 450 degrees Celsius. Pulsars. In 1933, astrophysicists Walter Baade and Fritz Zwicky introduced the concept of neutron stars, dense, compact remnants of supernova explosions. In 1965, radio astronomers Anthony Hewish and Samuel Okoye identified the inaugural observational evidence of a neutron star, a potent yet diminutive source of intense radio energy emanating from the center of the Crab Nebula, the remnants of the renowned daytime star supernova of 1054. Hewish and his associates at the University of Cambridge persisted in their quest for novel neutron stars and additional radio sources. Merely 2 years later, utilizing the newly developed, more sensitive 4-acre radio telescope situated west of Cambridge, Hewish's student Jocelyn Bell identified the inaugural rapidly pulsating radio star, pulsar, in the constellation Vulpecula, exhibiting a consistent pulse rate of 1.373 seconds. Bell and Hewish contemplated that the pulsar's remarkably consistent radio signal could indicate extraterrestrial intelligence, humorously designating the source as LGM1, meaning Little Green Men 1. By 1968, they and other astronomers had formulated a more credible explanation, partly owing to identifying a radio pulsar with a pulse rate of 33 milliseconds in the neutron star at the core of the Crab Nebula. Researchers identified pulsars as rapidly rotating neutron stars with intense magnetic fields emitting energy in particular directions, typically aligned with or near their rotational axis. When the rotating pulsar directs its emitted electromagnetic radiation toward Earth, it can activate radio telescopes, similar to a lighthouse's rotating beacon. Since then, scientists have identified thousands of pulsars, encompassing several hundred millisecond pulsars, such as the one in the Crab Nebula. In 1992, scientists deduced that fluctuations in the timing of signals from the pulsar PSRB 1257+12 were attributable to orbiting planets, signifying the inaugural instances of extrasolar planets. The image presents a high-resolution composite of the Hubble Space Telescope, red, and Chandra X-ray Observatory, blue, depicting the central region of the Crab Nebula, Messier 1, a remnant of a supernova explosion that occurred in 1054. The primary energy source is a pulsar, a swiftly rotating neutron star characterized by a 33 millisecond rotation period. Investigation of extremophiles. Astrobiology examines the origin, evolution, and distribution of life and habitable environments throughout the universe. It is a unique discipline as it possesses a singular data point to validate its existence. We are aware of only one instance of life in the universe, namely life on Earth, which is fundamentally analogous, relying on comparable RNA, DNA, and other carbon-based organic molecules. Searching for extraterrestrial life extends beyond the pursuit of complex organisms akin to our own. It explores alternative planetary environments conducive to the survival of Earth's most prevalent life forms, bacteria and other rudimentary organisms. Our planet, where we have markedly enhanced our comprehension of habitability in the last 50 years, is the optimal location to initiate the search for those conditions. In 1967, American microbiologist Thomas Brock published a seminal paper detailing heat-tolerant bacteria hyperthermophiles that thrived in the hot springs of Yellowstone National Park. He contested the dominant belief that the chemistry of life necessitates moderate temperatures for functionality. Brock's research catalyzed the investigation of extremophils, organisms that endure and flourish in extreme conditions. Researchers have since identified hyperthermophilic bacteria in extremely hot water near deep-sea hydrothermal vents, while psychrophiles flourish in temperatures near or below freezing. Researchers have discovered that certain forms of life can endure extreme temperatures, extreme acidity or alkalinity, elevated pressure, low humidity, and high levels of ultraviolet or nuclear radiation. The history of life on Earth unequivocally demonstrates to astrobiologists that life can thrive in diverse environments. Consequently, the notion of seeking evidence of past or present extremophiles or their habitable environments in extreme locales such as Mars, the deep oceans of Europa and Ganymede, or the frigid organic-rich surface of Titan is no longer as implausible as it previously appeared. Initial presence on the Moon. Following Yuri Gagarin's historic journey as the first human in space, the competition between the United States and the Soviet Union rapidly shifted towards the next significant objective: landing astronauts on the Moon and ensuring their safe return to Earth. The Soviet Union redirected the Vostok program to emphasize the development of larger rockets and landing systems necessary for lunar exploration and return. The objective in America was to surpass the Russians and fulfill the late President John F. Kennedy's 1961 aspiration of achieving this before this decade is out. From 1961 to 1969, the United States executed a succession of progressively sophisticated missions, commencing with the Mercury single astronaut flights, advancing to the Gemini two-person Earth orbital docking and rendezvous missions, and culminating in the three-person Apollo lunar expeditions. Apollo 8 accomplished a significant milestone in 1968 by dispatching the inaugural humans to orbit the Moon and observe the entirety of Earth and the lunar far side directly. This achievement was replicated in early 1969 with Apollo 10, a comprehensive rehearsal for a lunar landing that brought astronauts within 10 miles, 16 kilometers, of the lunar surface before their return to Earth. Concurrently, the Russians advanced in their clandestine lunar cosmonaut program. Numerous disastrous unmanned launch failures in 1969 considerably hindered their program, facilitating an American triumph. The triumph occurred on July 20, 1969, as the world observed astronauts Neil A. Armstrong and Edwin G. Buzz Aldrin were among the first humans to land, walk, and conduct activities on the Moon. Armstrong and Aldrin alighted on the primordial volcanic lava flows of the Mare Tranquillitatis impact basin, with age dating of the samples indicating they are 3.6 to 3.9 billion years old, and dedicated approximately 2.5 hours to sample collection and terrain exploration. Within less than 24 hours, they departed and reunited with Command Module pilot Michael A. Collins in lunar orbit for the 3-day journey home, hailed as global heroes. 2 seconds on the Moon. Merely 4 months after the triumphant mission of Apollo 11, NASA astronauts were once more traversing the lunar surface. On November 19, 1969, astronauts Alan Bean and Charles Pete Conrad directed the Intrepid lunar module for a precise landing near NASA's 1967 Surveyor 3 robotic lander, while Command Module pilot Richard Gordon orbited above. Conrad and Bean effectively exhibited precise landing accuracy by positioning their spacecraft within 600 feet, 180 meters, of Surveyor 3. Such precise landings would be essential for future Apollo missions. Conrad and Bean dedicated approximately 32 hours on the Moon, with nearly a quarter of that time spent outside, collecting samples and establishing experiments in the flat lava plains of Oceanus Procellarum, Ocean of Storms. Their most extensive expedition involved a trek to the Surveyor 3 probe, from which they removed several components and instruments for return to Earth. Surveyor 3 had remained on the lunar surface for more than 3 years. The retrieved components yielded comprehensive data regarding the prolonged effects of vacuum, intense solar radiation, and micrometeorite impacts on lunar surface apparatus. Remarkably, certain dormant bacteria on various surfaces successfully traveled to the Moon and returned, with tests indicating their viability persisted even after 3 years in the Moon's extreme vacuum and ultraviolet (UV) conditions. The extended time spent on the lunar surface enabled the Apollo 12 astronauts to gather approximately 75 pounds, 34 kilograms, of lunar samples, in contrast to the 48 pounds, 22 kilograms, collected during Apollo 11. These samples comprised soils, small rocks, fragments of boulders, and deposits from impact craters. Scientists examined the samples and determined that the dark volcanic rocks in the Procellarum basin are significantly younger, 3.1 to 3.3 billion years old, than those retrieved by the Apollo 11 crew from the Tranquillitatis basin, 3.6 to 3.9 billion years old. This indicates that the Moon possessed volcanic activity for a minimum of 1.3 to 1.5 billion years during its early history. The rocks in the Apollo 12 samples exhibit distinct chemical differences from those in Tranquillitatis. The samples comprise dark, glassy rocks and the initial specimens of breccia, a novel category of lunar rock formed from fragmented rocks that have been fused by impacts. Astronomy transitions to a digital format. Astronomy was a visual discipline for millennia, with practitioners depending on their acute eyesight and superior night vision to locate and describe celestial objects. 200 years after the invention of the telescope, the human eye remained the sole detector that was accessible to astronomers. The advent of astrophotography in 1839 equipped astronomers with enhanced light detection instruments, initially silvered glass plates, followed by sensitized photographic films. While it represented a significant advancement in data archiving and observational consistency, photography merely enhanced the capacity to capture light from dimmer astronomical sources. During World War II, advancements in radar and navigation electronics for aircraft and weaponry significantly enhanced the sensitivity of astronomical detectors. These advancements culminated in the invention of the first electronic switches, diodes, circa 1939, and the inaugural electronic amplifiers, transistors, in 1947. These devices depended on the characteristics of specific elements, such as silicon or germanium, which are neither true conductors like metals nor complete insulators. Such semiconductors are materials that typically do not conduct electricity, but can be induced to supplying the appropriate voltage or, in certain instances, merely by illuminating them. In 1969, American physicists Willard Boyle and George Smith at AT&T Bell Labs achieved a significant semiconductor breakthrough for astronomers, as well as for digital camera and cell phone users, by developing an array of semiconductors that transformed incoming light, photons, into analog voltage signals, which could subsequently be stored, amplified, and converted into digital numbers. The invention is termed a charge-coupled device, CCD, due to the coupling of incident light on the array with the resultant electrical charge. Astronomers quickly embraced CCDs upon their introduction in the 1970s and 1980s. Their output signal is directly proportional to the luminosity of the illuminating objects, and they possess a sensitivity 100 times greater than that of photographic film. CCD cameras have become standard apparatus for astronomical telescopes and space missions. Organic compounds in Murchison meteorite. A primary impetus for space exploration is the quest for extraterrestrial life. How do we perform such a search? One method is to identify the chemical elements present in life on Earth. Elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements, however, exist in numerous locations and environments across the cosmos, such as the interiors of stars, that are improbable to support life. A more effective strategy may involve searching for specific arrangements, molecules, rather than individual elements, which could provide evidence for the fundamental chemistry of life. Life on Earth relies on organic molecules. Certain organic molecules are straightforward, such as methane, CH4, methanol, CH3OH, and formaldehyde, H2CO, while others exhibit greater complexity, including proteins, amino acids, ribonucleic acid, RNA, and deoxyribonucleic acid, DNA. In the past 50 years, astronomers have detected numerous simple organic molecules in dense interstellar clouds, comet tails, icy moons, the rings of the outer solar system, and the atmospheres of Titan and the gas giants. On September 28, 1969, a meteor and fireball traversed the daytime sky, impacting the ground near the town of Murchison in Victoria, Australia. The region produced over 220 pounds, 100 kilograms, of meteorite specimens. Following a thorough examination of the samples, scientists declared in 1970 that the meteorite, belonging to the most archaic and rudimentary category of meteorites known as carbonaceous chondrites, encompassed several common amino acids. Subsequent research revealed that the Murchison meteorite comprised over 70 varieties of amino acids, in addition to numerous other simple and complex organic molecules. Life, as we understand it, necessitates liquid water, energy sources such as heat or sunlight, and plentiful, intricate organic molecules. Identifying amino acids in Murchison and other meteorites substantiates the hypothesis that essential life molecules can originate abiotically in settings like a solar nebula disk, comet, or planetesimal. Life may be scarce or plentiful in the cosmos, yet it manifests universally. Venera 7 successfully lands on Venus. Notwithstanding the collapse of their lunar cosmonaut program in 1969, the Soviet Union attained extraordinary accomplishments with their robotic probes on various planets. The Venera 3-6 missions to Venus, conducted from 1966 to 1969, did not reach the surface. However, they yielded sufficient data on the planet's atmosphere to allow mission controllers to develop future missions capable of enduring the severe conditions. Success was achieved with the launch of Venera 7, which on December 15, 1970, became the inaugural human-made object to land on and transmit data from the surface of another planet. Venera 7 descended through the atmosphere via parachute for 35 minutes before landing, transmitting data for an additional 23 minutes. At that time, the lander transmitted temperature data indicating the surface temperature was approximately 870 degrees Fahrenheit, 465 degrees Celsius, with the surface pressure estimated to be around 90 times that of Earth's surface pressure. The lander's survival under such extreme heat and pressure is remarkable. The triumph of Venera 7 established the foundation for a remarkable series of subsequent Soviet Venera landers, orbiters, and atmospheric probes from 1972 to 1985. The most ambitious long-term initiative of robotic exploration of Venus ever undertaken. The paramount discoveries included the initial images of the planet's rocky terrain captured when sunlight penetrated the dense cloud cover, as well as the inaugural comprehensive maps of mountains, ridges, plains, and other tectonic and volcanic formations created using radar imaging from the Venera 15 and 16 orbiters. The maps indicated that the planet's surface comprised rocks akin to the basaltic volcanic formations in Hawaii and Iceland. In addition to the extreme surface conditions, the Venera probes enabled planetary scientists to ascertain that wind speeds in Venus's middle and upper atmosphere surpassed 220 miles, 100 meters, per hour, significantly exceeding the planet's rotational velocity. One Venusian day is approximately 243 Earth days. The cause of the superrotation of Venus's atmosphere remains unidentified. However, it is a primary focus of current and forthcoming missions to study Venus, often referred to as Earth's twin. Lunar robotic sample retrieval. The Soviet Union's robotic space exploration initiative during the 1960s and 1970s accomplished a series of scientifically significant firsts in missions to the Moon, Venus, and Mars. Luna 16, Luna 20, and Luna 24 were among the most significant and technologically remarkable, representing the world's inaugural robotic sample return missions. These diminutive automatic stations were launched from Earth on a 5-day voyage to the Moon. Following a 3-day return journey and parachute descent, they executed an autonomous soft landing on the lunar surface, drilled shallow boreholes to obtain lunar samples, and launched small sample return capsules to Earth. Luna 16, launched in September 1970, was the inaugural autonomous sample collection and return mission, successfully retrieving 3.5 ounces, 100 grams, of lunar soil and rock fragments from the dark lava plains of the Mare Fecunditatis impact basin. Luna 20 replicated the achievement in 1972, acquiring 2 ounces, 55 grams, of samples from a luminous highlands area adjacent to Mare Fecunditatis, while Luna 24 accomplished the same in 1972-1976, retrieving 6 ounces, 170 grams, of samples from Mare Crisium, a lava-infused impact basin near the Moon's eastern edge. The Luna specimens enhanced the extensive Apollo-returned sample collection by incorporating distinct and unique lunar surface compositions and mineralogies. The Apollo and Luna samples collectively furnish essential data that underpins contemporary theories regarding the Moon's origin and evolution, including critical evidence supporting the giant impact hypothesis for its formation. The Soviet Luna sample return missions represented the most intricate robotic endeavors ever. Subsequently, scientists have executed additional sample return missions to collect materials from a comet tail, the Stardust mission, solar wind particles, the Genesis mission, and minute fragments of a near-Earth asteroid, the Hayabusa mission. The Luna sample return missions are among the most intricate planetary exploration endeavors ever undertaken, a feat rendered even more extraordinary due to their dependence on 1960s technology. Proposals and plans for forthcoming robotic sample return missions from various regions of the Moon, Mars, Venus, and near-Earth asteroids continue to exist. The initial Mars orbiters. Robotic planetary exploration has advanced over the past 50 years through increasingly audacious and technologically sophisticated space missions. The primary objectives were to master the navigation of remote probes in space, enabling them to conduct flybys of the Moon and other planets while transmitting data in the form of images and various measurements. The subsequent logical progression is to deploy orbiting satellites around other celestial bodies to study an alien environment and chart an extraterrestrial surface or atmosphere. NASA's Mariner 9 space probe was the inaugural satellite to advance planetary exploration by orbiting another planet. Mariner 9 reached Mars in November 1971 amid a widespread dust storm observed by astronomers. As the spacecraft's spectrometers collected data on dust characteristics and atmospheric temperatures, the probe's television cameras captured a monotonous dusty sphere, predominantly featuring a few dark patches emerging from the dust. Following nearly 1 Earth year in orbit, the dust had sufficiently settled, enabling the mission to map the planet's surface with unparalleled precision. The Mars depicted in the Mariner 9 images was a geological marvel featuring colossal volcanoes, the dark spots observed during the dust storm, vast tectonically formed canyon systems, ancient river channels, and numerous impact craters. The view of Mars, characterized by impact craters from the earlier Mariner flyby missions in 1965 and 1969, presented a striking contrast. In 1971, the Soviet Union seized the opportunity to deploy 2 Mars orbiters, designated Mars 2 and Mars 3. Both spacecraft entered orbit several weeks after Mariner 9 and provided valuable scientific data regarding the atmosphere and surface once the dust had settled. Both also deployed diminutive landers and miniature rovers to investigate the surface. Although neither lander succeeded, They were the inaugural human artifacts to collide with the Martian surface, gamma-ray bursts. Physicists investigating the spontaneous decay of radioactive elements at the onset of the 20th century identified three types of particles or radiation emitted by radioactive substances, including uranium and radium. Certain elements emit helium nuclei, referred to as alpha particles. Other entities, referred to as beta particles, emitted electrons or positrons with elevated energies. Physicists identified a third, higher energy form in various radioactive decay events, which they designated as gamma rays. Like X-rays, gamma rays constitute electromagnetic radiation characterized by extremely high energy and short wavelengths. In the late 20th century, physicists discovered that electrons surrounding an atom undergoing radioactive decay emit X-rays, whereas the atomic nucleus emits higher energy gamma rays. Physicists anticipated and detected the production of gamma rays during nuclear fusion bomb tests due to their generation by the nucleus. In the 1960s, the United States and the Soviet Union positioned gamma ray detectors in space to verify compliance with the 1963 Partial Test Ban Treaty. The U.S. satellites belong to the military's Vela series, capable of detecting gamma rays from any location in space. Commencing in 1967, satellites sporadically, several times annually, identified enigmatic short gamma-ray bursts, GRBs, enduring from milliseconds to several minutes, which were subsequently ascertained to originate from arbitrary directions in deep space. 1973, the military declassified the data and informed civilian scientists about the phenomenon. Gamma-ray bursts, GRBs, have confounded astrophysicists for decades because their energies significantly exceed those of gamma-ray events generated by radioactive decay or stellar nuclear fusion reactions. The intricate characteristics of gamma-ray bursts, GRBS, remained enigmatic until observations from NASA's Compton Gamma Ray Observatory in the 1990s elucidated their origin. Gamma-ray bursts, GRBs, are believed to originate from supernova explosions, the collapse of massive stars, or the merger of colliding neutron-star pairs. Like pulsars, the detonating star emits jets of concentrated energy directed toward Earth, producing gamma-ray bursts, GRBS. Gamma-ray bursts are the most violent and energetic phenomena in the universe. Pioneer 10 has reached Jupiter. Robotic exploration of the solar system predominantly concentrated on the inner solar system, particularly the Moon, Venus, and Mars, until the 1970s. Planetary scientists recognized that comprehending the solar system necessitated thorough close-range exploration of the outer solar system. Pilots 10 and 11 were specific missions at birth. Pioneer 10 launched on March 2, 1972, and its twin, Pioneer 11, launched on April 4, 1972. 1973 were nuclear-powered probes intended to investigate the characteristics of interplanetary space beyond Mars. Their findings indicated that dust and micrometeoroids in the primary asteroid belt do not substantially threaten future spacecraft. During its flyby, Pioneer 10 approached within 125,000 miles, 200,000 kilometers, of Jupiter's cloud tops, capturing photographs that disclosed significant detail about the planet's atmosphere. Pioneer 10 sustained its interstellar mission beyond Jupiter for another 30 years, transmitting its final signals in 2003. Pioneer 10, one of merely 5 spacecraft to achieve escape velocity from our solar system, continues to travel at over 7.5 miles per second and is currently more than 120 astronomical units from the Sun. Additionally, they initiated 3 others in the 1970s, typically progressing in the contrary direction. Pioneer 11, last contacted in 1995, is presently over 99 astronomical units away and is progressing toward the center of the Milky Way. Voyager 2 is located over 116 astronomical units away and continues to transmit sporadic fields and particle data from deep space. Voyager 1 currently holds the record at over 141 astronomical units and continues to transmit scientific data while traveling outward at a velocity exceeding 10.5 miles per second, 17 kilometers per second. The fifth mission to attain escape velocity from the solar system is the NASA New Horizons probe, launched in 2006. It passed Pluto in the summer of 2015 and is currently over 40 astronomical units from the Sun. Voyager 1 was the inaugural robotic envoy from Earth to exit the solar system. In 2012, the spacecraft traversed the heliopause, the demarcation where the Sun's tenuous solar wind integrates with the ambient interstellar medium. Martian Vikings. The brief yet successful mission of Mariner 9 in 1971 established the foundation for a new NASA initiative to investigate Mars with unprecedented detail. The Viking project sought to deploy 2 orbiters and 2 landers to Mars, thereby augmenting our comprehension of the red planet's surface, atmosphere, and potential as a historical or contemporary habitat for life. The Viking 1 and Viking 2 probes were launched in August and September 1975, arriving at Mars in June and August 1976, respectively. In the initial month of orbit, the Viking 1 team captured surface photographs, identified a secure location for the deployment of the nuclear-powered lander, and ultimately selected a level area referred to as Chrysae Planitia, Plains of Gold. On July 20, 1976, Viking Lander 1 landed, signifying the inaugural successful mission to the Martian surface. Viking Lander 2 successfully landed several months later, approximately 3,000 miles, 4,800 kilometers, distant in the flat and rocky Utopia Planitia. Project Viking, with an expenditure of approximately $1 billion, was the most intricate and costly Mars mission undertaken to that point, and it achieved remarkable success. The orbiters produced global surface maps with hundreds of meters or greater resolutions. These maps illustrated ancient water-formed valley networks, intricately stratified polar cap deposits, and specifics of Mariner 9's findings of more recent volcanic mountains and vast canyons. The hypothesis that early Mars could have been warmer, wetter, and more akin to Earth was founded on data from Viking orbiters. The landers established an enduring framework for Martian research. Meteorological experiments yielded comprehensive data on surface conditions and weather patterns detrimental to human beings. Crucially, landers' quest for organic molecules, possible indicators of life or at least of habitable conditions, yielded no results. The setback for astrobiologists was transient. It facilitated the refinement of new experiments for subsequent missions. Commencement of the Voyager Grand Tour. Astronomers and mission planners contemplating the deployment of robotic probes to the outer solar system in the late 1960s and early 1970s observed that Jupiter, Saturn, Uranus, and Neptune were aligning in a manner that could enable a single probe to utilize gravitational assists to traverse past all 4 gas giants during the 1970s and 1980s. NASA researchers were highly enthusiastic about the historic Grand Tour concept, which they ultimately executed through a new pair of missions named Voyager. Voyager 2, launched on August 20, 1977, reached Jupiter in mid-1979, Saturn in mid-1981, Uranus in early 1980, 1986, and Neptune in mid-1989. Voyager 1 was launched on September 5, 1977, on a rapid trajectory that would enable it to reach Jupiter in early 1979 and Saturn in late 1980. Voyager 1's mission encompassed only flybys of Jupiter and Saturn. The intention to conduct a close flyby of Triton, Saturn's substantial moon with a dense atmosphere, necessitated a trajectory adjustment, precluding subsequent encounters with Uranus and Neptune. The missions of Voyager 1 and Voyager 2 rank among the most exhilarating and successful endeavors in space exploration and general exploration. The probes facilitated new discoveries regarding the atmospheres, magnetic fields, and ring systems of the giant planets and their substantial moons, including Io, Europa, Ganymede, Callisto, Titan, and Triton, along with numerous smaller moons. The discoveries made by Voyager facilitated further findings at Jupiter and Saturn through the subsequent Galileo and Cassini orbiters and supplied the necessary data for future orbital missions to Uranus and Neptune. Like the pioneers, each Voyager possesses a message in a bottle, a golden record that encodes images, voices, and music, a cosmic time capsule conveying greetings from Earth to any future discoverer. In 1659, the Dutch astronomer Christian Huygens observed and elucidated Saturn's rings as a slender disk of material encircling the sixth planet. Until 1789, Saturn was perceived as the sole planet possessing a ring system. However, following the discovery of Uranus, the English astronomer William Herschel believed he observed a faint ring encircling that planet as well. Nevertheless, later visual and photographic examinations of Uranus failed to corroborate Herschel's assertion. Almost 2 centuries later, on March 10, 1977, the American planetary scientists James Elliott, Ted Dunham, and Douglas Mink were poised to observe Uranus transit in front of a comparatively bright star, an event referred to as an occultation. The team observed the event from the Kuiper Airborne Observatory, a telescope mounted on a NASA C-141A jet that conducted missions in the stratosphere above most clouds and atmospheric water vapor. In this manner, they could ascertain their presence in the correct location to observe the rare occultation. The occultation produced an exhilarating revelation. Uranus obscured the star on 5 occasions, resulting in a significant decrease in its luminosity. Subsequently, immediately following the star's re-emergence from the eclipse, it occurred 5 additional times. Elliott and his team's analysis indicated that the starlight drops transpired at an equivalent radial distance from Uranus on both sides of the planet. A faint set of narrow rings was discovered, indicating that the 7th planet is the second known planet with rings. Subsequent observations disclosed 4 additional narrow rings encircling Uranus, increasing the total to 9. During the 1986 flyby of Voyager 2, astronomers discovered 2 additional rings utilizing the Hubble Space Telescope. This indicated that the rings are exceedingly dark and likely composed of icy fragments ranging from centimeters to meters in size. The magnetic field of Uranus interacts with icy organic molecules, resulting in darker formations. Subsequently, Voyager data disclosed subtle rings encircling Jupiter and Neptune, affirming that all the gas giants in our solar system, not Saturn, are ringed planets. Charon. Situated almost 40 times farther from the Sun than Earth, Pluto presented significant observational challenges decades following its discovery by Clyde Tombaugh in 1930. Nevertheless, astronomers continued observing Pluto to gain further insights into its origin and characteristics. Astronomers performed numerous observations using telescopes at the Lowell Observatory in Flagstaff, Arizona, where Pluto was discovered. In June 1978, Lowell astronomer James W. Christie observed a bulge in several photographs of Pluto while analyzing a series of observations. Christie reported that the bulge shifted around Pluto's primary image. Subsequent analysis led him and his associate Robert S. Harrington to publish their findings regarding a satellite orbiting Pluto. Christie designated the moon Charon in tribute to his wife, Charlene, or Char, and after the mythological Greek ferryman of the deceased, explaining the pronunciation as Sharon rather than Charon. Charon's diameter is 750 miles, 1,207 kilometers, approximately half that of Pluto, rendering the Pluto-Charon system akin to a double-planet configuration. Charon's surface is primarily composed of water ice and potentially minor quantities of hydrated ammonia, contrasting significantly with Pluto's surface, which is predominantly comprised of nitrogen and methane ice. In 2005, the Hubble Space Telescope's observations of Pluto and Charon uncovered an unexpected finding: additional moons. In 2011 and 2012, the Hubble Space Telescope identified two smaller satellites, Nix and Hydra, orbiting the center of mass of the Pluto-Charon system, named after Greco-Roman mythological figures. When the NASA New Horizons probe traversed their vicinity in July 2015, anticipation surged regarding the appearance of these remote celestial bodies. Active volcanism on Io. During its 1973 flyby of Jupiter, Pioneer 10 captured remarkable images of the gas giant but failed to obtain high-quality views of its major moons, Io, Europa, Ganymede, and Callisto, which Galileo discovered in 1610. The Voyager 1 probe, which conducted a flyby of Jupiter in March 1979, was equipped with a significantly more advanced and higher-resolution camera system. Nonetheless, its flyby trajectory would bring it nearer to the planet and its sizable moons. The Voyager 1 encounter with Jupiter unveiled numerous revelations, the most significant of which was the identification of active volcanic plumes and lava flows on Jupiter's innermost moon, Io. Initially discernible as silhouettes in remote images, over 400 active volcanoes populate the surface of Io in high-resolution, close-range observations. Io's volcanoes emit new, molten lava flows extending tens to hundreds of miles, frequently tinted by molten sulfur at varying temperatures, and they occasionally erupt violently, projecting an umbrella-shaped cloud of ash and rocky fragments hundreds of miles into space. The images captured by Voyager 1 and 2 demonstrated that Io is the most volcanically active body in the solar system. On March 8, 1979, scientists captured a photographic record of volcanic plumes erupting on Io. However, what is the rationale? Io, Europa, and Ganymede orbit Jupiter in a 4:2:1 orbital Laplace resonance, resulting in gravitational interactions that induce periodic perturbations and slight eccentricities in their orbits. Conversely, Jupiter's gravitational force attempts to induce synchronous rotation in its moons, ensuring that the same hemisphere consistently faces the planet, akin to Earth's moon. Consequently, intense tidal forces perpetually compress and elongate the moons, particularly the innermost Io, and the resultant friction from this compression generates internal heat. Tidal heating has entirely liquefied it, vaporizing all its water and ice, resulting in global volcanic eruptions that perpetually renew the satellite and emit sulfur and dust into a vast toroidal disk surrounding Jupiter. Unyielding tidal forces have transformed it into a tormented realm. Rings of Jupiter. Pioneer 10 and 11, the inaugural space probes to approach Jupiter, conducted comprehensive measurements of the planet's magnetic field and energetic particle environment during their flybys in 1973 and 1974. The data indicated unusual alterations in the protons and electrons within Jupiter's equatorial plane, adjacent to the orbits of Amalthea and the other inner moons. This led us to consider that an object, possibly a ring, was absorbing particles at such a distance from the planet. Prompted by this mystery, mission planners for the Voyager 1 flyby of Jupiter in March 1979 devised specialized observations to capture long-exposure photographs of the area. The photographs delighted the team by revealing a narrow ring system orbiting Jupiter, establishing it as the third recognized giant planet with rings. During its flyby in July 1979, the Voyager 2 probe captured additional images of Jupiter's ring system. The NASA Galileo Jupiter Orbiter, along with the Cassini and New Horizons missions, captured more detailed images during their flybys of Jupiter, revealing that the ring system comprises 4 primary components. The toroidal halo ring is nearest to the planet. The primary ring is luminous and slender, measuring 19 to 186 miles, 30 to 300 kilometers in width. The 2 diffuse gossamer rings are more distant and linked to the minor moons Amalthea and Thebe. In contrast to the rings of Saturn and Uranus, Jupiter's rings are composed of dust rather than ice. Impacts from comets or asteroids seem to have ejected dust and small rocky fragments from the moons Metis and Adrastea, forming the main and halo rings. Microscopic particles are ejected from Amalthea and Thebe, creating the delicate rings. Bands and other formations suggest that small embedded moonlets or aggregates of ring material contribute to and define the rings. Jupiter's rings are likely youthful and perpetually renewed by new impacts, since one of the inner moons is expected to eject dust only after a lifespan of approximately 1,000 years. The spacecraft produced this mosaic of Jupiter's ring system from the Galileo-Jupiter orbiter, observed edge-on, and oriented towards the Sun while traversing Jupiter's shadow behind the planet. A sea on Europa. Since its discovery by Galileo in 1610, limited information has been acquired regarding Jupiter's second-largest moon, Europa. Europa is engaged in a 4 to 2 to 1, Io to Europa to Ganymede, orbital resonance, suggesting it is subject to fascinating tidal forces. Telescope spectroscopy indicated that Europa possesses a luminous surface coated with water ice. Concerning the intricate characteristics of Europa's surface, the slate was nearly entirely devoid of information when the Voyager 1 and 2 probes conducted the initial comprehensive exploration of Jupiter's system. The discoveries made by Voyager at Europa were significant. The planet-sized moon, marginally smaller than Mercury, possesses one of the smoothest surfaces in the solar system. Nevertheless, a complex and interwoven network of fissures and low elevations permeates the smooth surface, ostensibly segmenting it into icy plates that shift about one another. This was an initial indication that the surface constitutes a relatively thin, tectonically active ice shell floating atop a substantial layer of liquid water, an ocean beneath. Additional evidence indicating that Europa is an oceanic world arises from observing a scarcity of impact craters on its surface, implying that it is geologically youthful and undergoing active resurfacing. The NASA Galileo-Jupiter orbiter facilitated a more comprehensive examination of Europa throughout its mission from 1995 to 2003. Observations from the Galileo spectrometer of saline mineral deposits within certain cracks and fractures provided further evidence of the existence of a deep ocean. These are the types of mineral deposits that would develop from the evaporation of saline ocean water. Galileo's magnetic field data indicated that Europa's subsurface possesses electrical conductivity, suggesting saline ocean water beneath the icy crust. Current data indicates that Europa possesses a global ocean approximately 60 miles, 100 kilometers, deep beneath its relatively thin icy crust, which ranges from 6 to 20 miles, 10 to 30 kilometers, in thickness. Future missions that will orbit or land on Europa's crust and potentially penetrate it will yield direct evidence of this ocean. Astrobiologists are currently enthusiastic about Europa's potential as a habitat for life. Thanks to tidal heating from Jupiter, the influx of organic molecules from comets and asteroids, and the presence of ample liquid water, it is possible that Europa's ocean may eventually be found to be a habitable or potentially inhabited environment. Albert Einstein's theory of general relativity, which was developed in the early 20th century, is fundamentally characterized by the curvature of space and time in the vicinity of extremely massive objects. The gravitational field of massive foreground objects would bend light from distant objects due to the curvature of space-time, as predicted by Einstein and others. Arthur Stanley Eddington, a British astrophysicist, verified the prediction in 1919 by observing that stars visible near the Sun during a solar eclipse were slightly displaced from their normal positions. In the 1930s, Einstein and other astronomers, including the Swiss-American astronomer Fritz Zwicky, continued investigating this phenomenon. They hypothesized that more massive objects, such as galaxies, could bend and amplify light from distant objects, like how a lens bends and magnifies ordinary light. Nevertheless, it took several decades for astronomers to discover observational evidence of gravitational lensing. In 1979, astronomers at the Kitt Peak National Observatory in Arizona discovered the first instance of what appeared to be twin quasars, two active galactic nuclei situated close to one another in the sky. The light of the two quasars was bent and split into two parts by the strong gravitational field of a foreground galaxy. There have been numerous additional examples of gravitational lensing discovered since that time, and researchers have proposed three potential mechanisms for the effect to occur. Strong lensing is a phenomenon that arises when distinct, multiple, or partial images are generated, typically in the form of an arc. Small and subtle shifts in the positions of stars or galaxies over vast regions have been used to detect weak lensing. During microlensing events, a large foreground mass, such as another star or galaxy, temporarily increases the brightness of random faraway stars, or planets, by functioning as a lens. Initially, researchers discovered and investigated gravitational lenses as serendipitous, unforeseen occurrences. Nevertheless, scientists have deliberately conducted astronomical surveys to identify gravitational lensing events. The objective of these surveys is to obtain precise measurements of the characteristics of galaxies that are located at a great distance and would not be visible without amplification lenses. Additionally, these surveys will examine the characteristics of the lensing galaxies and clusters, such as their mass. The Pioneer 10 and 11 missions, which were launched in 1972 and 1973, were designed to conduct the first reconnaissance of the outer solar system and beyond. Pioneer 10's initial encounter with Jupiter occurred in 1973, paving the way for Pioneer 11's flyby of the giant planet in 1974 to 1975. Nevertheless, Pioneer 11 was on a trajectory that could utilize Jupiter's gravity to propel it toward its first-ever encounter with Saturn in 1979, in contrast to Pioneer 10. The Pioneer 11 probe successfully encountered Saturn, passing within approximately 13,000 miles, 21,000 kilometers, of Saturn's cloud tops on September 1, 1979. The mission, which included cameras, magnetic field and charged particle instruments, cosmic dust particle and radiation counters, and other scientific instruments, offered planetary scientists their initial glimpses of the environment in and around the ringed planet. Pioneer missions were precursors to the more ambitious Voyager probes exploring the outer solar system. For instance, Pioneer 11 traversed Saturn's ring plane during the Saturn flyby to ascertain whether the spacecraft was at risk of being struck by small dusty or icy ring particles. They did not, which allowed mission planners to guide Voyager 2 through the same region of the rings to place it on a trajectory that would facilitate subsequent encounters with Uranus and Neptune. Other discoveries at Saturn were also made due to Pioneer 11 data. These include the observation of Triton, the largest moon with an atmosphere, having an extremely low temperature of 90 kelvins, which may be too cold for life. Detailed maps of Saturn's magnetic field were also created, which is a large charged particle structure similar to Jupiter's magnetic field in some ways. Pioneer 11 is on an escape trajectory from our solar system, similar to Pioneer 10. It is currently located over 83 astronomical units from the Sun and is on its way to the center of the Milky Way galaxy. The probe was lost from communication with the spacecraft in late 1995. However, it still bears a plaque resembling Pioneer 10s. This plaque will be an informative greeting for any future galactic neighbors who discover the probe. Astronomy and space exploration are captivating and thrilling subjects. However, scientists have not been compelled or incentivized to disclose their discoveries, or more specifically their failures, to the public in recent history. Presenting their findings at scientific conferences or publishing their results in academic journals or books was sufficient. Many even exhibited arrogance regarding their work. The public would not comprehend it, so why disclose it? Although media coverage of the Apollo missions in the 1960s and 1970s significantly increased the public interest and international appeal of space exploration, it was still difficult for the general public to remain informed about the most recent observations and discoveries. The three primary broadcast TV networks in the United States primarily aired entertainment and news programs. The Public Broadcasting Service, PBS, was the fourth network, and it aired a few exceptional general interest science programs, but did not produce any space-related programming. Carl Sagan, a charismatic and thought-provoking American astronomer, hosted a new television series in 1980 that concentrated on astronomy and human space exploration. Cosmos. A Personal Voyage was an enormous success. It was the most watched PBS series in the world, with an audience of over 500 million individuals. Sagan engaged the public in a lively and educational dialogue about the most recent observations and theories related to the most profound questions we contemplate. What is occurring in the celestial spheres? What was the source of it all? What is the purpose of our presence? Are we the only ones? Sadly, Sagan encountered substantial opposition from many of his scientific peers due to his tireless efforts to promote the importance of space exploration and science. According to reports, he was denied membership in the National Academy of Sciences due to the personal animosity of other scientists. Nevertheless, a new generation of planetary scientists and astronomers, many of whom were raised on Cosmos, have embraced Sagan's ideals and legacy. These ideals have been widely promoted by members of the Planetary Society, a public space advocacy organization he assisted in establishing in 1980. The scientific community considers them indispensable for the public's comprehension and communication of science in the contemporary era. The Pioneer 11 robotic probe's 1979 flyby of Saturn was a preliminary study for the NASA Voyager 1 and Voyager 2 probes launched in 1977. These probes were designed to conduct a more comprehensive and ambitious investigation of the planet's atmosphere, moons, rings, and magnetic field. In November 1980, Voyager 1 flew past Saturn, and Voyager 2 followed closely behind in August 1981. The Voyager Saturn encounters have significantly enhanced our understanding of the Saturn system's diverse bodies and processes. Details regarding the impact cratering record, composition, and geologic histories of the large icy moons Iapetus, Rhea, Tethys, Dione, Enceladus, Mimas, and Hyperion were disclosed through high-resolution imaging analyses. The Voyager images revealed 7 small new moons of Saturn, several of which were embedded in a ring system that was vastly more intricate than previously believed. We found that Saturn's rings are composed of thousands of individual rings and ringlets, which are separated by thin gaps and maintained in order by the gravity of several shepherd moons that orbit in the ring system. The telescopic and Pioneer 11 discoveries that Saturn's largest moon, Triton, has a thick and hazy atmosphere were confirmed by Voyager data. Triton is the sole moon in the solar system with a thick primarily composed of nitrogen, as its atmosphere has a surface pressure over 50% higher than Earth's. The orangish hue of Triton's haze was influenced by minute quantities of methane, ethane, propane, and other organic molecules, some of which were anticipated to exist as surface liquids at the planet's frigid temperatures. Nevertheless, Voyager's cameras could not penetrate Titan's haze. Toto observed the surface. Those discoveries would occur approximately 15 years later during the Cassini-Saturn orbiter and Huygens Titan lander missions. Voyager 1's planetary exploration mission concluded at Saturn. The probe's trajectory was diverted from its grand tour path, which included a potential flyby of Pluto in the late 1980s, to bring it close enough to Titan for a detailed study of its early Earth-like atmosphere. Voyager 1 remains operational at approximately 120 astronomical units from the Sun, rendering it the most distant object humans have ever sent into the cosmos. The dream of human spaceflight, as rocketry pioneers Konstantin Tsiolkovsky and Robert Goddard first envisioned, has never been about one-way trips into space. Rather, we truly comprehend the full extent of the influence of individuals who travel beyond our planet when they return home and share their adventure stories, scientific findings and samples with the rest of us. However, the rocket must transport return capsules, parachutes, and supplies to transport individuals, or payloads, to and from space. The Vostok, Mercury, Gemini, and Apollo astronaut programs utilized each return capsule and system only once. Engineers have long considered reusable rocket designs to reduce the cost of transporting people and equipment into space and establish access to space as a routine, similar to commercial airline travel. This was the impetus for NASA's creation of the National Space Transportation System, or Space Shuttle, in the 1970s. The space shuttles employed two reusable solid-fuel rockets, a large expendable tank to fuel the orbiter's engines during launch, and a reusable vehicle for the crew and equipment, with rocket engines for ascent and airplane-like wings for descent. 5 orbiters, Columbia, Challenger, Discovery, Atlantis, and Endeavour, transported 355 astronauts into low Earth orbit, approximately 250 miles, 400 kilometers, above the surface, between the initial launch in 1981 and the 2023 135th and final launch in 2011. Some of the astronauts were transported on multiple flights. 14 astronauts were killed in the course of their duties, 7 in the Challenger, which exploded upon launch in 1986, and 7 in the Columbia, which disintegrated during re-entry in 2003. The Space Shuttle's missions were incredibly successful, even though they never became routine, and the hope of more economical access to space was never realized. Shuttles were indispensable for constructing the International Space Station, repairing and maintaining the Hubble Space Telescope, launching numerous Earth and planetary satellites, and conducting significant space-related biological, astronomical, and Earth sciences research. After the retirement of the Space Shuttle fleet, NASA intends to construct a new rocket system that can transport astronauts beyond the shuttle's low Earth orbit, either to the Moon or to new destinations such as Mars and its moons and near-Earth asteroids. The discovery of the Uranian rings in 1977 and the Jovian rings around Jupiter in 1979 was the first indication that 3 of the 4 giant planets had ring systems. William Lassell, a British astronomer who had previously discovered the large moon Triton of Neptune in 1846, also observed a ring encircling the planet. However, the observation was never verified. The quest to determine whether Neptune possessed rings lasted more than 140 years. In the 1960s, several astronomers began to observe Neptune's stellar occultations as distant stars appeared to eclipse the planet and slip behind it. The ring system of Uranus had been discovered through a stellar occultation, and astronomers believed that the same method would reveal rings around Neptune. In 1982, 2 distinct groups, one in New Zealand and the other in Arizona, reported the detection of potential rings or partial ring arcs around Neptune, based on an analysis of observations made in 1968 and 1981. However, the majority of the results were ambiguous and not repeatable. Then, in 1984, two groups of astronomers from Arizona and France were able to observe the same occultation event. For the first time, they independently confirmed the detection of telltale dips in starlight near the planet, a strong indicator of the possibility of rings. It was not until August 1989 when Voyager 2 conducted a flyby of Neptune. Nevertheless, the spacecraft cameras offered conclusive evidence of the existence of Neptune's rings. Voyager images and additional stellar occultation data identified 5 distinct, generally faint, dark rings on Neptune. These rings were named after prominent astronomers who made significant contributions to the early study of Neptune: Galle, Leverrier, Lassell, Arago, and Adams. The Adams ring is the furthest from Neptune and contains at least 5 brighter parts or arcs than the rest. Previous ground-based astronomers have detected and identified these arcs as potential rings. The rings of Neptune are dark and dusty, more resembling those of Jupiter than those of Saturn or Uranus. However, Neptune's rings are currently believed to be relatively young remnants of a recent impact breakup of small inner moons or moonlets, similar to the rings of Uranus. Astronomers are still actively pursuing the cause of the perplexing arcs in the Adams ring. The prevailing theory regarding the formation of our solar system posits that an immense cloud of gas and dust, which may have been the remnants of a supernova explosion from a previous generation star, gradually began to gravitationally contract, spin, and flatten into a circular disk of condensing material. The Sun absorbed over 99.99% of the mass in this solar nebula disk. Jupiter composed most of the remaining material. We inhabit a minute portion. If this model is accurate, it should have also occurred near other stars, particularly Sun-like stars prevalent in the Milky Way galaxy. Direct starlight is 1 million to 1 billion times brighter than any reflected light from disks or planets orbiting them, rendering the search for disks, rings, or dust halos around stars impossible. The French astronomer Bernard Lyot, who invented a specialized telescopic attachment known as a coronagraph in 1930, made a critical breakthrough by utilizing it to block direct sunlight, enabling astronomers to observe the Sun's upper atmosphere or corona. By employing a smaller version of the device, astronomers could detect faint light from objects near a star and block out direct light from the star. The Infrared Astronomical Satellite, IRAS, a joint NASA, Dutch, and British space telescope, conducted the first all-sky survey of infrared heat energy emitted by cosmic objects, 1983. According to IRAS data, researchers hypothesized that the unusual excess of low-temperature infrared heat energy surrounding the young Beta Pictoris results from dusty or rocky material orbiting the star. In 1984, astronomers at Las Campanas Observatory in Chile employed a Lyot-style coronagraph to verify the theory. They observed a solar nebula encircling another star, which was surrounded by a beautiful, dusty, and rocky circumstellar disk that extended approximately 400 astronomical units from the star's center. The Beta Pictoris disk is currently one of numerous circumstellar disks believed to be young solar systems in the process of forming. In 2008, astronomers conducted an even closer imaging of Beta Pic and discovered a giant planet that orbited the star at a distance of only 8 astronomical units. This planet is approximately 8 times the mass of Jupiter and is one of the first extrasolar planets to be directly imaged. NASA engineers employed the gravity of Saturn's ringed planet to direct the Voyager 2 space probe during its 1981 flyby, which culminated in an encounter with the massive planet Uranus in January 1986. This was the third stop on Voyager 2's grand tour of the outer solar system and is the sole instance of a spacecraft encountering Uranus, its icy rings, moons, and bluish atmosphere. Uranus, which is tilted on its side and rolls around the Sun, was discovered in 1781 by the English astronomer William Herschel. To obtain the precise gravity assistance required to propel the spacecraft onto Neptune, the Voyager. 2 mission planners were required to guide the spacecraft within approximately 50,000 miles, 81,000 kilometers, of the upper cloud layers of Uranus. The trajectory enabled a close flyby of the small inner moon Miranda and more distant views of the geology of the 4 other large moons, Ariel, Umbriel, Titania, and Oberon. The encounter was exceedingly successful, resulting in numerous novel and perplexing discoveries regarding the Uranian system. Planetary scientists have discovered that Uranus has a magnetic field that is both strong and peculiarly tilted about the planet's sideways spin axis. This field is comparable to Saturn's but weaker than Jupiter's. The imaging data identified 11 new moons and provided detailed images of the 9 dark rings previously identified from Earth-based telescopic measurements. According to Voyager 2 data, the aquamarine color of the Uranian cloud tops is caused by minute quantities of methane. Based on the analysis of density and other data, the planet is believed to have an icy mantle and a rocky metallic core that is equivalent to Earth's size beneath the hydrogen and helium-dominated atmosphere. The discovery that Uranus and Neptune are ice giants rather than gas giants is an enduring legacy of the Voyager 2 encounters. The spacecraft's close pass by the tiny moon Miranda, which is only 300 miles, 480 kilometers wide, was the highlight of the encounter for many. The images revealed a landscape unlike any other observed in our solar system before or since, which featured a patchwork quilt pattern of giant fractures, ridges, and cliffs interspersed with bland, cratered, icy terrain. The same massive impact event that may have toppled Uranus appears to have disassembled Miranda and reassembled it asymmetrically. According to stellar evolution models, a star will ultimately terminate its existence in a massive explosion known as a supernova after converting all of its helium, assuming it is sufficiently massive, approximately 8 to 10 times the Sun's mass. According to astronomers, a supernova explosion is believed to occur in the Milky Way galaxy approximately once every 50 years. The majority are too far away to be observed or obscured by galactic plane dust. For centuries, Chinese astronomers documented numerous guest stars, such as a supernova in 185 and a daytime star supernova in 1054, culminating in the formation of the Crab Nebula. Tycho Brahe conducted comprehensive observations of a supernova in the constellation Cassiopeia in 1572, and Johannes Kepler composed an entire book in 1606, which detailed a bright supernova in Ophiuchus that had occurred 2 years prior. The most recent known stellar explosion in our galaxy is Kepler's supernova of 1604. The blue supergiant star, Sanderlic, negative 69 degrees 202, suddenly exploded on February 23, 1987, resulting in supernova 1987A, which allowed modern astronomers to observe a supernova up close. The explosion occurred 168,000 years prior in the Large Magellanic Cloud, one of the Milky Way's dwarf satellite galaxies. However, it took that long for the light to reach Earth. The star's brightness increased by approximately 4,000, allowing it to be visible to observers worldwide for over 6 months before losing its brightness. Supernova, 1987. A was employed by astronomers as a grand cosmic experiment to gain insight into high-energy and stellar evolution processes. Ultraviolet, X-ray, optical, and infrared telescopes in space, as well as optical and infrared telescopes worldwide, observed the event and its aftermath. The core collapse model for supernova explosions was confirmed by the detection of neutrinos by multiple observatories 3 hours before the visible explosion. In recent years, astronomers have observed the shock waves from the primary explosion collide with a shell of gas previously ejected from the dying progenitor star. Several celebrities have passed away in dramatic, violent circumstances. Whether these cataclysmic events have also resulted in the destruction of planets and their inhabitants and the potential timing of the next supernova in our galaxy is a matter of speculation. It appears that we are past due. Our ancestors were inspired, awed, and revered by the night sky. Thousands of stars, including the grand sweeping arch of the Milky Way, could be observed unaided by the naked eye on a clear, moonless night, even from the cities. Nevertheless, the relationship between humans and the night sky has been significantly altered by the emergence of modern civilization, particularly the widespread use of electricity for artificial illumination and the expansion of major cities and urban centers. Rather than thousands of stars, most individuals in industrialized countries can now typically observe only hundreds of stars on a clear night. Residents of major cities may be fortunate enough to observe a handful of airplanes and 10 or 20 stars, but the Milky Way is not visible. The night sky has lost its awe-inspiring quality for most individuals, transforming into a featureless, faintly glowing and dull background. Light pollution, which modifies the natural outdoor light levels through artificial light sources, is the cause of this nocturnal cosmic dulling. Light pollution can harm the health of nocturnal ecosystems, interfere with astronomical observations of faint sources, and obscure fainter stars for individuals residing in cities or suburbs. Lighting a home or building at night is intended to illuminate the structure, not to consume energy in kilowatts to illuminate the night sky. Additionally, it is economically inefficient. The International Dark Sky Association, IDA, was established in 1988 by a group of concerned citizens in response to the increasing global issue of light pollution. The organization's mission is to preserve and protect the nighttime environment and our heritage of dark skies through quality outdoor lighting. IDA currently has approximately 5,000 members worldwide who collaborate with city and local governments, businesses, and astronomers to increase awareness of the importance of dark skies and assist in implementing lighting solutions that are more energy efficient and cost-effective, thereby reducing light pollution. The utility of major observatories near large cities, such as the Mount Wilson Observatory, which is perched above Los Angeles, continues to be limited by the effect of light pollution, despite some notable successes in establishing ordinances and building codes that decrease it. In the present day, individuals construct new telescopes in remote deserts or on isolated, dark mountaintops to escape the increasing brightness of the night sky. The Voyager 1 and 2 missions were launched in 1977 at a fortunate time, as a rare alignment of Jupiter, Saturn, Uranus, Neptune, and Pluto could have enabled a space probe to gravitationally slingshot from one planet to the next and conduct flybys of all 5 planets with minimal additional propulsion. Advocates for this grand tour of the outer solar system recognized that such an opportunity would not arise for another 176 years. Voyager 1 abandoned the Pluto flyby option in favor of a closer flyby of Saturn's moon Titan. However, Voyager 2 successfully completed the initial reconnaissance of all 4 giant planets. The spacecraft executed a 24,000-mile, 38,000-kilometer flyby of the large icy moon Triton during its final stop on the Grand Tour in August 1989 at Neptune. A great deal of beauty and mystery in the Neptune system was revealed by the encounter between Voyager 2 and Neptune. The atmosphere of the planet, which contained hydrogen, helium, and methane, was significantly more dynamic than that of Uranus in 1986. The Great Dark Spot, a giant cyclonic storm, was surrounded by white clouds and dark and light blue belts, which were analogous to Jupiter's Great Red Spot. Active geysers of icy nitrogen, water, and carbon dioxide are present on the relatively youthful surface of Triton, which erupts nitrogen into the moon's thin atmosphere of nitrogen carbon monoxide and methane. This discovery was made by planetary scientists. A new large moon, Proteus, was discovered by scientists near the planet. The moon was named after the shape-shifting Greek sea god. It was 250 miles, 400 kilometers, in diameter. 5 additional small moons were identified and characterized by scientists during the flyby. We are gradually devising strategies to deploy orbiters to Uranus and Neptune to further develop Voyager's initial discoveries. Early 20th century astronomers such as Vesto Slipher and Edwin Hubble determined the Doppler shifts of distant galaxies in our expanding universe due to advancements in telescopes, spectrometers, and photographic plates. The distances to those redshifted galaxies could be estimated using Hubble's law. It was a slow process. By the 1950s, only approximately 600 galaxies had estimated distances. Nevertheless, the measurement of redshifts for over 30,000 galaxies was made possible by the 1970s and 1980s as a result of the development of dedicated all-sky galaxy surveys, advancements in digital detectors, such as charge-coupled devices or CCDs, and the use of larger telescopes. At last, we can commence the process of mapping the universe. John Huchra, a Harvard-Smithsonian Center for Astrophysics CFA astronomer and a pioneer in galaxy mapping, has been utilizing the results of numerous large-scale galaxy redshift surveys to elucidate the structure of the cosmos. The initial CFA redshift survey was conducted from 1977 to 1982, and the subsequent survey was conducted from 1985 to 1995. Geller and Huchra reported in 1989 that the distribution of galaxies was not uniform. Instead, a structure now referred to as the cosmic web clusters galaxies into vast filamentary structures that encircle giant voids that contain a few galaxies. One of the largest structures in the universe, the Great Wall, was named by Geller and Huchra. It spans over 500 million light-years in length and 300 million light-years in width. Astrophysicists have a potent working model for forming these vast patterns in the universe. Galaxies and larger patterns develop from minute irregularities in the distribution of matter in the early universe. These peculiar events may occur in certain versions of this model due to extremely early inflation, which occurred within the first 10 to 32 seconds following the Big Bang. Matter was smeared into web-like filaments that may have clumped together to form galaxies during this period. In the early 17th century, the first astronomical telescopes were developed, which allowed astronomers to explore the skies. Subsequently, larger and more sophisticated instruments were developed, facilitating the discovery of remarkable things about the solar system, galaxy, and universe. Consequently, astronomers have consistently recognized that even the largest telescopes on Earth possess 2 significant deficiencies. Initially, the resolution is significantly reduced by the shimmering and twinkling of our atmosphere, which is significantly lower than the theoretical limit of a large telescope. Secondly, the ultraviolet and infrared regions of the spectrum are obstructed by our atmosphere, rendering it difficult or impossible to observe from the ground at critical wavelengths. Astronomers began advocating within NASA for a dedicated space-based telescope to address the limitations imposed by the introduction of space satellites in the 1960s. Lyman Spitzer, an American astronomer, was the primary advocate for an orbiting space telescope. He spearheaded a critical grassroots lobbying campaign to secure the project's essential support and funding. The Hubble Space Telescope, HST, which was named after astronomer Edwin Hubble, was granted approval in 1978 after successfully navigating numerous bureaucratic obstacles and establishing a partnership with the European Space Agency. About 350 miles, 570 kilometers above the Earth's surface, the Space Shuttle Discovery launched HST into low Earth orbit in April 1990. Shortly after its launch, HST identified a significant defect in its primary mirror design. Fortunately, the telescope was serviced by Space Shuttle astronauts, and 5 shuttle missions were conducted between 1993 and 2009 to repair and upgrade critical instruments and components. Consequently, HST functions as a cosmic time machine that employs spectroscopy and CCD imaging to ascertain the nature and age of our universe. By the standards of today's giant telescopes, HST is merely a medium-sized telescope. However, its consistent full-spectrum and clear-sky perspective on the cosmos has allowed it to fulfill the aspirations of Spitzer and other early supporters and fundamentally transform contemporary astronomy and astrophysics. In February 1997, the Space Shuttle Discovery released the Hubble Space Telescope during a servicing mission. The telescope is approximately 350 miles, 560 kilometers, above the Earth's surface. It has a diameter of approximately 8.2 feet, 2.5 meters, and a length of approximately 43 feet, 13.1 meters, slightly longer than the average school bus. Galileo was the first to recognize that Venus had phases when he examined it through his initial astronomical telescope in 1610. Unlike the observations of other astronomers, Galileo's observations of Venus did not reveal any specific features or markings, in contrast to his studies of the Moon and Jupiter. In line with expectations, recent telescope observations and space missions such as the Soviet Venera orbiters and landers have demonstrated that Venus's surface is obscured by a thick atmosphere of carbon dioxide, smooth clouds, and sulfuric acid hazes. Radio waves can be perceived through clouds and haze, which is fortunate. In fact, terrestrial meteorologists employ radar weather mapping instruments to capitalize on radio waves that reflect off raindrops and snowflakes and pass through clouds. In the 1960s, astronomers discovered that radio waves could penetrate the clouds of Venus by bouncing radar signals off the planet using the Arecibo radio telescope. This enabled the identification of surface markings and the identification of the planet's rapid, 243 Earth days, backward rotation. The Arecibo findings justified the development of orbital radar mapping missions to Venus. The Soviet Venera 15 and 16 orbiters, which were launched in 1983 to 1984, were the first successful missions. They mapped approximately 25% of Venus's northern hemisphere, revealing mountains, ridges, faults, volcanoes, and other landforms. The NASA Magellan mission, which was even more ambitious than Venera's radar mapper, was inspired by Venera's findings. Magellan, which was launched in 1989 by the space shuttle Atlantis, arrived in 1990 and systematically mapped 98% of the surface from pole to pole. The Magellan data depicts the landscape of Venus, which ranges from deep valleys to tall mountains. In addition, they provide geologists with images of various landforms formed by volcanoes, tectonic plates, impacts, and erosion. Large Hawaiian-style shield volcanoes, pancake-shaped volcanic domes, and vast lava plains were discovered by Magellan scientists. Additionally, they identified channels thousands of miles long, carved by molten rock with a very low viscosity. They also identified extensive networks of ridges and troughs, which suggest tectonic activity but not Earth-like plate tectonics. The scarcity of impact craters suggests that most of the planet was resurfaced by massive lava outpourings approximately 500 to 750 million years ago. Venus has been, and continues to be, just as active over geologic time, even though it is not Earth's twin. 1964, the cosmic microwave background was discovered, which had substantial implications. It illustrated the feasibility of testing theories like the Big Bang through observations. A new generation of astronomers developed an interest in observational cosmology, which involves the precise measurement of specific characteristics of the universe to facilitate a comprehensive understanding of its origin and evolution. Nevertheless, to achieve precision, Conducting these measurements from space is imperative. NASA's ongoing Explorer small satellite program was a perfect platform which commenced in 1958 with the Explorer-1 discovery of the Van Allen radiation belts. The Cosmic Background Explorer, COBE mission, was approved by NASA in the 1980s and launched into Earth orbit in 1989. Astronomers developed the mission concepts in the 1970s. To gradually and precisely construct a map of the variations in cosmic background radiation across the entire sky, COBE employed highly sensitive infrared and microwave radiation detectors. Cosmologists declared the initial map to be finalized in 1992, and the final results were thrilling. COBE discovered a dipole signature that was only 1/1000th of the sky's brightness. This was due to the Doppler shift induced by our galaxy's speed compared to the rest of the universe. After that signal was eliminated, the subsequent largest COBE variation was caused by the faint microwave emission of our Milky Way galaxy. Astronomers were delighted to discover that there were still some minor variations, which were minute fluctuations in the background radiation.